Picture this, a world without factories, without mass production, without the hum of machinery that defines our modern existence. Every object you touched, every piece of clothing you wore, every meal you ate, it all came from the hands of skilled artisans, using tools crafted with care and purpose. These weren't just instruments, they were extensions of human ingenuity, born from necessity and refined over generations. In the Middle Ages, life wasn't powered by electricity or engines, but by the quiet, persistent work of tools that have largely faded from memory. Yet these tools built cathedrals that still touch the sky, forged armor that defied swords, and wove tapestries that told stories for centuries. They were the unsung heroes of an era defined not by what people had, but by what they could create. Today, we're going to rediscover 30 of these incredible instruments, each one a key that unlocked some aspect of medieval life. From the heavy plow that turned stubborn earth into fertile fields, to the delicate astrolabe that guided sailors across uncharted seas, these tools were more than functional objects. They were marvels of design, each imbued with the wisdom of its maker and the spirit of its time. We'll explore not only how they worked, but the secrets behind their creation, the techniques blacksmiths used to temper steel, the ways carpenters shaped wood without a single nail, and the methods weavers employed to turn simple threads into complex patterns. These weren't just tools, they were solutions to the challenges of survival, community, and creativity. So join us on a journey back through time, a journey into workshops lit by forge fire, fields bustling with harvesters, and studios where art and utility met. By the end of this exploration, you won't just see these tools as relics of the past. You'll understand them as testaments to human resilience and imagination. You'll gain a new appreciation for the medieval world and perhaps even see echoes of its craftsmanship in the objects we use today. This is more than a history lesson. It's an invitation to witness the humble origins of the world we've built, one tool at a time. To truly grasp the significance of these medieval tools, we must first step into the world that created them. This was an era stretching across 1,000 years, from the fading echoes of the Roman Empire to the dawn of the Renaissance, a time where life was intimately tied to the land and the rhythm of the seasons. There were no factories humming in the distance, no global supply chains delivering ready-made goods. Survival and community prosperity hinged on one crucial element: the ability to make things by hand. Every object, from the grandest castle gate to the simplest wooden spoon, was the product of immense skill, patience, and a deep, hard-won understanding of materials. This reliance on manual craftsmanship meant that artisans were the bedrock of society. The blacksmith, the carpenter, the weaver, the potter, these weren't just jobs, they were vital roles often passed down from parent to child, master to apprentice. Knowledge wasn't written in manuals but lived in the muscles, in the subtle glance of an experienced eye judging the color of heated metal, or in the feel of a specific type of wood grain under a practiced hand. A master blacksmith knew the secret to tempering steel by the way the cooling metal sang. A carpenter understood which local woods were best for bearing weight or resisting rot, knowledge gained from generations of trial and error. This was a world of trade secrets in the truest sense, where the techniques for creating a sharper blade, a stronger joint, or a more vibrant die were guarded treasures, the intellectual property of a guild or a family. The tools themselves were born from this intimate relationship between the maker and their environment. The iron for a hammerhead might be smelted from ore dug from a nearby hillside. The handle for an adze would be fashioned from a branch of a locally felled oak, shaped to fit the user's grip perfectly. There was no such thing as disposable or mass-produced. Resources were too precious and labor too intensive. A tool was crafted to last a lifetime, often repaired and rehandled, becoming an heirloom that carried the marks and stories of its use. This deep connection meant every tool was more than just an implement. It was a concentrated piece of human ingenuity, a physical manifestation of cultural values and technological understanding. It represented a solution to a specific challenge of medieval life, refined over decades to achieve a perfect balance of form and function. Understanding this context, the value of skill, the scarcity of resources, and the profound connection between the artisan and their work is the key that unlocks the true genius and enduring legacy of the tools we're about to explore. Now, if you were to step into that dim, smoke-filled workshop, your eyes would first be drawn to the fire, but your ears would tell you the true story, the ringing, percussive chorus of hammer on metal. And at the center of that symphony, its solid, unshakable stage, was the anvil. This wasn't just a block of metal, it was the very soul of the smithy, the foundational partner to every act of creation. Think of it as the blacksmith's silent apprentice, an unyielding surface that absorbed countless blows yet never complained, never broke, and never wavered in its duty. Its sheer weight, often hundreds of pounds, was a statement of purpose, anchoring the chaotic energy of the forge into focused, productive work. But crafting an anvil was a monumental task in itself, a true test of a master smith's skill. They weren't simply cast in a single pour. The finest were built up from wrought iron, a material prized for its toughness and ability to absorb impact without cracking. The most critical part, the face where all the hammering happened, was then welded on as a separate plate of hardened steel. This was the secret, a tough, shock-absorbing body with an incredibly hard, durable surface that could resist denting and maintain a smooth plane for centuries. Getting that weld perfect, with no flaws or weak spots, was a black art known only to the most experienced artisans. A poorly made anvil would simply disintegrate under the relentless punishment, but a well-made one became a generational asset, passed down from master to apprentice, its surface becoming a testament to a lifetime of work. And every single contour of that surface had a specific, vital purpose. The large, flat area known as the face was the main stage, used for the majority of shaping and flattening. But step to one end and you'd find the horn, that iconic, cone-shaped projection. This wasn't for show, it was a former for bending and drawing out curves, perfect for shaping the metal rim of a wagon wheel or the elegant sweep of a scythe blade. On the other end, usually a flat, square tail called the heel, you'd find various holes. The hardy hole, a square opening, acted as a secure mount for a variety of specialized tooling like cutters and bending forks. The smaller, round punch hole was used for precisely driving holes through hot metal. A master smith knew his anvil like a musician knows their instrument, dancing around it, moving the metal across its different features with an intuitive grace. He didn't just hit metal on an anvil, he played it, using the right surface for the right task with flawless, efficient rhythm. This profound relationship between the smith and his anvil elevated it beyond mere tool into the realm of symbol. It represented stability, resilience, and the transformative power of skilled labor. In many cultures, it was considered sacred, a place where raw, chaotic earth, in the form of ore, was brought to be ordered and given purpose by fire and human will. To be anvil hard was the highest compliment for one's character. While the hammer gets all the dramatic attention, it was the anvil that truly did the work, providing the resistance necessary to shape the world. Every nail that held a roof, every hinge that hung a door, every sword that defended a kingdom, and every plowshare that turned the soil began its life being forged upon this most essential and enduring of medieval tools. But to understand just how revolutionary the heavy plow truly was, we have to look at what came before it. For centuries, farmers across Europe relied on a much simpler tool known as the adze or scratch plow. Picture a sturdy, pointed piece of wood, sometimes tipped with iron, that would be dragged through the soil. It was effective enough for the light, sandy soils of the Mediterranean, where it originated, simply scratching a shallow groove into the earth for seeds. But it had a critical limitation. It couldn't truly turn the soil. It just stirred the top layer, leaving the dense, compacted earth beneath untouched. This made it nearly useless in the vast, fertile plains of northern Europe, where the soil was a heavy, dense, and often wet clay that would simply cling to a simple adze and bring the whole operation to a frustrating halt. The heavy plow changed everything because it was engineered specifically to conquer this challenging terrain. Its most ingenious component was the moldboard, that curved, metal or wooden panel mounted behind the cutting share. As the plowshare sliced vertically into the tough sod, the moldboard would catch the cut strip of earth, lift it, and then slowly, deliberately, roll it over to one side. This single action was an agricultural miracle. It didn't just make a scratch, it actively aerated the soil, bringing nutrient-rich subsoil to the surface and burying weeds and the previous year's stubble underneath, where they would decompose and fertilize the land naturally. This process created those iconic, long, deep furrows and the raised ridges between them, a landscape that actually helped with drainage in those notoriously wet northern fields, preventing waterlogging that could drown young crops. The construction of such a powerful tool was a community effort, a marriage of different crafts. The massive frame, designed to withstand immense pulling forces, was the work of a master wheelwright or carpenter, expertly fashioned from unyielding hardwoods like oak or ash. But its bite came from the blacksmith, the sharp, pointed plowshare that cut the earth, and the coulter, a vertical knife mounted ahead of the share that made the first clean, slicing cut through the turf. Forging these large, complex iron components required significant skill and resources, making the heavy plow a substantial investment for a village. It was often owned communally, a shared treasure that would be used by all the farmers in a field strip system. And this is where the plow's impact rippled far beyond the field. Its efficiency didn't just mean a little more food, it fundamentally reshaped society. With a single heavy plow and a team of oxen, a farming family could cultivate vastly more land than ever before. This surplus of grain could support larger populations and even free up some people from farming altogether to pursue other trades in growing towns. The need for powerful draft animals to pull these heavier plows also encouraged the use of horses, which were faster and more efficient than oxen, especially after the parallel development of the horse collar, which allowed them to pull without choking. The heavy plow, in essence, was more than a tool. It was an engine of economic and social change, turning the once impenetrable clay soils of northern Europe into the breadbasket that would fuel the rise of medieval kingdoms. Now, if the anvil was the heart of the blacksmith's world and the plow the muscle of the field, then the loom was undoubtedly the nervous system of medieval society, a complex, rhythmic machine that literally wove communities together. While we might take our clothes and fabrics for granted today, in the Middle Ages, producing cloth was one of the most labor-intensive and vital processes of all, a true measure of a region's wealth and sophistication. Before the loom could even be touched, however, came the monumental task of preparing the fiber. For wool, this meant shearing, washing, and then the endless carding, brushing the fibers between two spiked paddles to align them, before they could be spun into thread on a spindle or treadle wheel. For linen, it was even more arduous, requiring the flax plant to be retted, broken, scutched, and heckled to separate the precious inner fibers from the woody stalk. This preparatory work, done overwhelmingly by women in the home, could take hundreds of hours to produce enough thread for a single bolt of cloth. The loom itself was where this patient preparation met transformative engineering. The great innovation of the medieval period was the horizontal loom, a massive wooden frame that allowed the weaver to sit and use foot pedals to control the sequence of the warp threads. This was a quantum leap over the older, vertical looms. Its key components worked in a beautiful, synchronized ballet. The heddles were the conductors of this orchestra, a series of cords or metal loops, each holding an individual warp thread. By pressing down on different pedals, the weaver could raise specific sets of these threads, creating a temporary space called the shed. In that fleeting opening, the weaver would swiftly pass the shuttle, a boat-shaped tool holding the weft thread, from one hand to the other. Then, with a sharp pull of the beater, a heavy frame holding a comb-like reed, they would slam the new weft thread tightly against the previous ones, compacting the weave. This sequence, pedal down, shuttle through, beat, repeat, was performed thousands of times, a hypnotic rhythm that slowly built up the fabric inch by painstaking inch. The true artistry, the closely guarded secrets of the weaver's guild, lay in the patterns. By programming a specific order into the pedals that raised certain warp threads, incredible designs could emerge from the monotony of the plain weave. A skilled weaver could create intricate herringbones, twills, and even elaborate pictorial scenes for tapestries. The choice of fiber was another layer of this secret knowledge. Wool from different sheep breeds had varying qualities. Some were coarse and perfect for hard-wearing cloaks, while others were fine and soft for garments of the nobility. Linen, spun from flax, produced a cool, strong fabric prized for undergarments and summer wear. And then there was silk, the ultimate luxury, imported at great expense along trade routes from the East and reserved for the most elite and ecclesiastical vestments. But the process didn't end with the weaving. The final secret weapon in the medieval textile arsenal was dyeing. This was alchemy, transforming dull, off-white fabrics into vibrant symbols of status and identity. The colors came from the world itself. Madder root, when carefully processed, produced a spectrum of rich reds and pinks. Woad leaves were fermented in vats of urine to create a stunning blue, a color so valuable that its production was strictly controlled by guilds. Walnut shells yielded deep browns, and weld plant a bright yellow. The dyer's skill was in knowing not just the source, but how to prepare a mordant, a metallic salt bath, often using alum, that would fix the dye to the fabric and prevent it from washing out. A bolt of scarlet wool or deep blue linen was not just fabric, it was a testament to a deep chemical understanding of the natural world, a valuable commodity that could be traded across continents. From the humble, homespun wool of the peasant to the brilliant, silk-woven tapestries that adorned castle walls, the loom was the engine of an entire economy and a canvas for breathtaking art, proving that necessity could indeed be the mother of the most beautiful inventions. While the heavy plow was turning the fields and the loom was weaving society's fabric, the most fundamental act of medieval life was happening daily inside the home. The transformation of hard, inedible grain into life-sustaining flour. This crucial task fell to one of the most ancient and essential tools in human history, the quernstone. Imagine starting your day not by reaching for a pre-made loaf, but by spending hours grinding enough wheat or rye just to bake bread for your family's single daily meal. This was the reality for countless households, a relentless rhythm of labor that defined the very cycle of survival. The quern was more than a tool. It was the heartbeat of the hearth, the uncelebrated engine that powered every person, from the lowest serf to the highest lord, for without its gritty, constant work, society itself would have simply ground to a halt. The design of the quern was a masterpiece of straightforward, effective engineering, refined over millennia. It consisted of two simple, circular stones. The lower stone, called the bedstone, remained perfectly stationary. The upper stone, known as the runner stone, was the one that was turned by hand. A peg in the center of the bedstone acted as a pivot, fitting into a hole in the runner stone, ensuring it rotated perfectly in place without wobbling off course. The user would pour a handful of grain into this central hole, and as the runner stone was turned, the grain would be caught between the two abrasive surfaces and slowly, inexorably, be crushed and ground its way outward towards the edges, emerging as a coarse, warm flour that was collected on a cloth or in a bowl placed beneath the stones. The motion was circular, repetitive, and physically demanding, a task that built strong muscles and required immense patience. But the true genius of the quern, the secret to its effectiveness, lay in the stone itself. Not just any rock would do. The ideal material was a specific type of volcanic rock, like basalt or lava quartzite, prized for its natural hardness and, just as importantly, its vesicular texture, a slightly porous, honeycombed surface filled with tiny, sharp crystals that acted like millions of microscopic teeth. This inherent abrasiveness meant the stone would naturally wear in a way that maintained a rough, efficient grinding surface. Over time, however, even the best stone would become smooth. This is where the art of dressing the quern came in. Using a smaller, pointed hammer stone, the user would carefully peck a series of radial grooves called harps from the center of the stone out to the edge. These grooves weren't just decorative, they acted like channels, directing the ground flour outward and providing cutting edges that dramatically increased the grinding efficiency, turning a smooth, worn surface back into a voracious, grain-chewing machine. This vital, time-consuming labor was overwhelmingly the domain of women. While men worked the fields to grow the grain, it was the women's responsibility to process it and transform it into food. It was often done communally, a chance for conversation and song to alleviate the monotony of the work, but it was never optional. The output of a hand quern was frustratingly small. It could take several hours of continuous grinding to produce enough flour for a single day's bread for a family. This daily grind, a phrase we still use today, born from this very act, was a constant reminder of the fragility of life. A broken quern stone or a lack of grain to put in it meant immediate hunger. The sound of grinding stones was the soundtrack of daily medieval life, a low, rhythmic rumble emanating from every home. The flour it produced was dark, filled with bits of grit from the stone itself, which slowly wore down teeth over a lifetime. Yet this humble, gritty flour was the absolute cornerstone of nutrition. It was baked into the dense, dark loaves that provided the bulk of calories for the entire population. Every piece of bread, every bowl of pottage, every bite of sustenance connected a person directly to the patient, grueling labor of the quern. It was a tool that required no forge, no complex assembly, and no great strength, but it demanded everything in terms of time and perseverance. In its simplicity, we see not just a method for making flour, but the enduring story of perseverance, the quiet, relentless determination to turn the raw materials of the earth into the very substance of life, one slow, circular motion at a time. While the rhythmic grind of the quernstone provided the soundtrack of the hearth, the percussive chip, chip, chip of another tool provided the melody of construction, shaping the very world medieval people lived in. If you were to walk onto a bustling medieval building site or a noisy shipyard, one of the most distinctive tools you'd see in action was the adze. At first glance, it might look like someone took an axe and gave it a curious twist, setting the blade at a perfect 90-degree angle to the handle. But this was no mere modification. It was a deliberate and brilliant reinvention of force and function. Where an axe is designed to deliver powerful, splitting blows directly in line with the swing, the adze was engineered for something far more nuanced, a controlled, arcing, slicing motion that could peel away thin, precise layers of wood, transforming a rough-hewn log into a smooth, functional surface. The magic of the adze lay entirely in its unique geometry and the way a skilled craftsperson wielded it. A carpenter would stand over a log, gripping the long handle with both hands, and swing the blade in a downward arc towards his feet, stopping it just short to shave off a perfect curl of wood. It was a dance of incredible coordination and trust in one's own skill. This action allowed for a level of control that was simply impossible with a standard axe. It could hollow out a log to create a perfect trough for a water channel or a feeding trough for animals. It could shape the massive, curved timbers needed for the ribbed hull of a cog or a gnar, ships that would carry traders and explorers across oceans. It could smooth the surface of a plank for a tabletop or a church pew, leaving a characteristic scalloped pattern that is still a telltale sign of hand-adzed work today. Mastering this tool was a rite of passage for any woodworker, and the true secret wasn't just in the strength of the swing, but in a deep, almost intuitive reading of the wood itself. A master knew how to work with the grain, not against it. Cutting against the grain would cause the blade to catch and tear, leaving a rough, splintered surface. Cutting with the grain allowed the adze to make a clean, slicing cut that left the wood smooth and ready for finishing. This required an understanding of how different types of wood behaved, the tough, interlocking grain of oak versus the softer, straighter grain of pine. The tool itself was a product of collaboration between the woodworker and the blacksmith. The woodworker would often fashion the handle for a perfect, balanced grip, while the smith was responsible for the heart of the tool, the blade. Forging an adze blade required expert tempering. It had to be hard enough to hold a razor-sharp edge through hours of work, yet flexible enough to withstand the immense shock of impact without chipping or shattering. This combination of brute force and delicate precision made the adze a powerful symbol of medieval craftsmanship itself. It was the key tool for the shipwright, whose adze-defined hulls would brave the North Sea. It was indispensable to the cooper, using it to shape the staves that would hold wine and ale. It was used by the wheelwright, the cartwright, and the millwright. The distinctive marks it left behind are like the signature of the artisan, a permanent record of their skill and labor etched into the wood. In an age before power planers and sanders, the adze was the primary instrument for turning nature's raw, rough timber into the refined, purposeful shapes of civilization. It represented a perfect partnership between human ingenuity and the material world, a tool that demanded not just muscle, but a profound respect for the character of the wood it was shaping. While the adze excelled at shaping wood from the outside, another tool was mastering the art of working from within the auger. Think of it as the medieval equivalent of a powered drill, but one powered entirely by human perseverance and a cleverly designed twist. In a world built on wooden joints and pegged connections, the ability to create a clean, precise hole was absolutely paramount. You couldn't simply nail or screw pieces together as we do today. The primary fasteners were wooden pegs or tree nails, and to use them, you first needed a perfectly sized hole. From the sturdy staves of a barrel holding precious ale to the massive timber frames of a great hall, the auger was the unsung hero that made it all hold together. The genius of its design was in that elegantly twisted metal bit, which we now recognize as the archetypal screw shape. This spiral flute or feed screw was the auger's secret weapon. As the craftsperson turned the wooden T-handle, the sharp spurs at the tip of the bit would score the circumference of the hole. Then, the twisted body of the bit did two crucial jobs simultaneously. Its sharp edges carved out the wood from inside the hole, while the spiral acted like a conveyor belt, efficiently pulling the chips up and out of the deepening cavity. This self-ejecting feature was vital, preventing the tool from becoming jammed with waste material and allowing it to bore far deeper and faster than any simple pointed awl could ever manage. The physical motion required was a steady, rhythmic turning combined with firm, consistent downward pressure, a skill that built immense strength in the arms and shoulders of carpenters, shipwrights, and coopers. But the true heart of the auger, the element that made this simple tool so effective, was its bit, and that was the exclusive domain of the blacksmith. Forging an auger bit was a test of a smith's skill in working with iron and steel. The entire bit had to be tough to resist the tremendous torsional stress of being twisted, but the cutting edge needed to be made of hardened, high-carbon steel to hold a razor-sharp edge. The smith would often weld a piece of steel just onto the cutting lips of an iron bit, a technique that conserved expensive steel while delivering superlative performance. The final, most delicate step was the precise shaping and sharpening of the spurs and the cutting lips. If these were even slightly misaligned or dull, the auger would wander off course or require Herculean effort to turn, rendering it nearly useless. A masterfully crafted auger bit was a prized possession, often passed down through a family of woodworkers. This humble tool's impact on medieval life is almost impossible to overstate. It was the key that unlocked advanced joinery. With a reliably straight hole, a craftsman could drive a dry, hardened wooden peg into a slightly smaller hole in another piece of wood. As the peg absorbed moisture from the air and the surrounding wood, it would expand, creating a joint that was not only incredibly strong, but also flexible enough to withstand the shifting and settling of a building over centuries, a principle we can still admire in the timber-framed structures that stand today. Beyond grand architecture, the auger was essential for crafting the daily objects of life. It bored the holes for chair legs, the bungholes in barrels, the axle holes in cartwheels, and even the finger holes in tools. It allowed for the working of bone and antler, materials used for everything from delicate needles to elaborate chess pieces. In the relentless, twisting motion of the auger, we see the quiet, persistent force of medieval innovation, a simple solution that, turn by turn, helped bore the foundations of the modern world. If the loom itself was the grand stage for the medieval weaver's performance, then the shuttle was undoubtedly its star performer, the nimble dancer that flew across that stage with breathtaking speed and precision. This small, deceptively simple tool was the critical link between the patient preparation of thread and the creation of actual cloth. Picture a narrow, boat-shaped piece of polished wood, perhaps the length of your forearm, gracefully curved to slice effortlessly through a forest of vertical warp threads. Its entire purpose was one of elegant efficiency, to carry the weft thread, the crosswise thread that literally weaves the fabric together, from one side of the loom to the other in the blink of an eye. Before its invention, weavers had to pass the weft thread through the shed by hand, a slow and laborious process that limited both the speed of production and the width of the cloth that could be reasonably made. The shuttle changed all of that, transforming weaving from a painstaking craft into a more dynamic, rhythmic, and productive industry. The genius of its design was in the details, each one a solution to a specific physical challenge. The most obvious feature is its boat-like shape, which wasn't just for aesthetics. The pointed, polished ends were essential for piercing through the narrow opening between the raised and lowered warp threads without catching or snagging on any individual fiber. A single rough edge or a splinter could break a critical warp thread, undoing hours of meticulous setup. but the true secret to its smooth operation often lay hidden inside. Many shuttles were carefully weighted, sometimes with a small piece of lead or simply by being crafted from a denser wood. This added mass gave the shuttle just enough momentum to be thrown or passed through the shed with a single, fluid motion, allowing it to coast all the way to the other side where the weaver's waiting hand would catch it. This is where we get the term flying shuttle, though that specific innovation with a mechanical hammer came much later. In the medieval period, it was the weaver's own skill and muscle memory that gave the shuttle its flight. And then there was its core function, carrying the thread. A channel ran down the center of the shuttle, holding a bobbin or a spindle onto which the weft thread was wound. As the shuttle flew through the shed, this thread would pay out smoothly and evenly from one end, leaving a clean line of weft in its wake. The consistency of this payout was vital. Too loose, and the fabric would be sloppy and weak. Too tight, and it would pull the edges of the cloth inward, distorting the entire piece. A master weaver knew the exact tension needed for different types of thread, the springy resistance of wool versus the slick glide of linen, and would often adjust the shuttle's path or the way the thread was wound on the bobbin to compensate. The tool itself was a deeply personal object. A weaver might spend hours carving and sanding their own shuttle from a favorite piece of fruitwood or boxwood, shaping it to fit their hand perfectly, perhaps even etching their mark into it. It became an extension of their body, a partner in the rhythmic, almost meditative dance of weaving. Foot down to change the shed, shuttle through, a sharp pull of the beater to pack the thread home, and repeat. This rhythm, accelerated by the shuttle, is what allowed for the dramatic increase in textile production that would fuel trade and clothe nations. This humble, polished piece of wood was more than a tool. It was the key that unlocked the loom's full potential, turning patient skill into tangible prosperity. Now, if you were to look at a magnificent medieval timber-framed house or a piece of furniture that has survived for centuries, you might marvel at its sturdiness and wonder how it was all held together without a single nail or screw in sight. The answer lies not in a tool you can hold in your hand, but in a concept, a meeting of two pieces of wood so perfectly engineered that it formed a bond stronger than the materials themselves. This is the mortise and tenon joint, the absolute cornerstone of medieval woodworking. It's a connection so fundamental, so brilliantly simple, that its invention predates recorded history, but its mastery during the Middle Ages allowed craftsmen to build structures that literally reached for the heavens. This wasn't just a way to stick two bits of wood together. It was the very language of construction, a grammar of joinery that allowed for endless complexity and unparalleled strength. The principle itself is beautifully straightforward. On one piece of wood, the craftsman would carve a perfectly square or rectangular projection. This is the tenon, essentially a wooden tongue. On the receiving piece, he would meticulously chop out a cavity of exactly the same dimensions. This is the mortise, the mouth waiting to receive that tongue. When the two are brought together, the tenon slides snugly into the mortise, creating a flush, seamless union. But the true magic, the secret that separated a novice from a master, was in the fit. A perfectly executed mortise and tenon joint is shockingly tight. It shouldn't go together easily. It requires a firm tap from a wooden mallet to seat it home. That satisfying thunk was the sound of a connection that would last for generations. This incredible precision was achieved not with lasers or digital calipers, but with the expert eye of the craftsman, guided by a set of marking tools and brought to life with his most trusted implements, a set of razor-sharp chisels and a heavy mallet. The creation of a single joint was a symphony of controlled force and delicate precision. First, the layout. Using a ruler and a scoring knife, the woodworker would mark the exact boundaries of both the tenon and the mortise. Then, with a saw, he would carefully cut the shoulders of the tenon, the parts that would seat flush against the receiving timber, ensuring the joint was not just strong but also visually perfect. The bulk of the waste wood on the tenon would be removed with a series of skillful saw cuts, but the mortise hole was the real test of patience and skill. Using a series of increasingly wider chisels, the craftsman would stand over the timber and, with a series of precisely angled mallet blows, slowly and methodically chop down into the wood, removing tiny chips with each strike. He had to work from both sides of the timber to prevent the wood from splintering out on the back face, and he had to constantly check the depth and squareness of the hole to ensure the tenon would enter straight and true. The final fitting was an art form in itself. A craftsman would often shave mere whiskers off the tenon with a finely set plane or a sharp knife, testing the fit over and over until it was perfect. A joint that was too loose would wobble and fail. One that was too tight could split the precious timber, ruining weeks of work. This pursuit of perfection meant that the secrets of the mortise and tenon were closely guarded within guilds and workshops. A master knew that the strength of the joint didn't just come from the fit, but from the orientation of the grain. He knew that for a joint that would bear immense vertical weight, like those in a cathedral roof, the tenon had to be cut from a specific part of the log to maximize its long grain strength. He knew the subtle tricks, like slightly chamfering the edges of the tenon to help it start its journey into the mortise without bruising the edges. And perhaps most importantly, he understood the power of wood's natural hygroscopic properties. The joint was assembled while the wood was in its seasoned, dry state. Over time, as the timber absorbed atmospheric moisture, both the tenon and the mortise would expand, but the tenon, being completely surrounded, would expand outward, locking itself into its socket with a force no metal fastener could ever hope to match. This self-tightening feature is a primary reason why so many medieval structures still stand solid today, long after any iron nail would have rusted away to dust. The applications of this joint were limitless, a testament to its versatility. It was the hidden skeleton inside every piece of furniture, from the humblest stool to the most ornate linen fold chest. It held together the wheels of carts and wagons, enduring the brutal shocks of unpaved roads. It was the critical connection in the soaring timber frames of barns, halls, and cathedrals, where massive oaken beams were joined high in the air to create spans that defied logic. In shipbuilding, it was used to join the keel to the stem and stern post, the very backbone of a vessel that had to withstand the relentless pounding of the sea. The mortise and tenon joint was more than a technique, it was a philosophy of building. It represented a deep respect for the material and a profound understanding of physics, demonstrating that the strongest bonds are not forced, but crafted with patience, skill, and a perfect fit. It allowed medieval craftsmen to think in 3 dimensions, to visualize and construct a world of incredible complexity and beauty, one perfectly fitted joint at a time. While the auger mastered the art of boring inward and the mortise and tenon joint perfected the meeting of 2 pieces, another tool was the undisputed champion of shaping wood from the outside in, removing material with a graceful, controlled aggression that was unlike any other tool in the workshop. This was the draw knife, a tool that looks deceptively simple, a long, sharp blade with a handle on each end, but in the hands of a master, it became an instrument of incredible subtlety and power. Its fundamental principle was a complete reversal of almost every other cutting tool. Instead of pushing the blade away from the body, as you would with a plane or a chisel, the draw knife was pulled directly toward the user, harnessing the stronger muscles of the back and shoulders to make long, sweeping, controlled cuts that could peel away thin, continuous ribbons of wood with astonishing speed and precision. This unique pulling action was the source of its greatest strength, an unparalleled level of control and feedback. As the craftsman pulled the blade toward their chest, they could feel the resistance of the wood through the handles, sensing the changing density of the grain, the presence of a knot, or the approach of the end grain in real time. This immediate tactile connection allowed for constant, minute adjustments in the angle and pressure of the cut. By slightly rotating the wrists, the user could change the angle of the blade's bevel, allowing it to slice deeper for rough, rapid stock removal, or ride almost parallel to the surface for a final, whisper-thin shaving that left the wood glassy smooth. This ability to transition from brute force to delicate finesse without ever switching tools made the draw knife incredibly versatile, the go-to implement for transforming a rough, split log into a beautifully curved chair leg, a perfectly tapered barrel stave, or a comfortably ergonomic tool handle. The true secret to wielding a draw knife effectively, however, was a deep, almost spiritual conversation with the wood itself. A master craftsperson didn't just see a piece of timber, they read its story in the pattern of its growth rings and the direction of its fibers. Cutting against the grain with a draw knife would result in a rough, torn surface full of ugly digs and splinters, but drawing the blade with the grain allowed it to slice cleanly between the wood fibers, lifting away a continuous, almost translucent shaving and leaving behind a surface so smooth it often needed no further sanding. This required an intuitive understanding of how grain could swirl and change direction around knots and branches, a knowledge earned through years of experience and more than a few ruined pieces. The tool was often used in conjunction with a shave horse, a specialized foot-operated vise that securely clamped the workpiece at a perfect height, freeing both of the craftsman's hands to focus entirely on the delicate art of the pull. And just as the user's skill was vital, so too was the quality of the tool itself, a product of the blacksmith's forge. A draw knife blade was not a simple piece of sharpened metal, it was a carefully engineered object. The best were forged from high-carbon steel, which could be heat-treated to a hardness that would maintain a razor edge through hours of demanding work, yet remain tough enough to resist chipping if it encountered a hidden nail or a stone embedded in the wood. The smith had to carefully draw out the steel to create the long, slender blade, then weld the tougher iron handles to the ends, ensuring that connection was flawless and could withstand the immense pulling forces. Finally, the cutting edge had to be honed to a precise bevel, typically around 25 degrees, a perfect compromise between sharpness for easy cutting and strength to support the edge. The handles themselves were often crafted by the woodworker, shaped from comfortable, grippy woods like beech or apple, and fitted over the tangs, making the tool a true collaboration between the smith's strength and the woodworker's touch. In the finished products of the medieval world, the legacy of the draw knife is everywhere, even if its marks are often hidden. Every smooth, curved surface on a piece of furniture that feels good in the hand likely started with this tool. The graceful bends of a Windsor chair bow, the concave interior of a wooden bowl, the precisely tapered spokes of a wagon wheel, all were born from the rhythmic, pulling motion of the draw knife. It represented a perfect fusion of human anatomy and tool design, leveraging our natural strength to perform work that required both immense power and delicate control. It was a tool that demanded respect, for its sharp edge was inches from the user's body, but it rewarded that respect with the ability to reveal the beautiful forms hidden within a rough piece of wood, proving that true craftsmanship often involves a confident, controlled pull, not just a push. But if the anvil was the stage and the hammer the lead actor, then the forge was the entire theater, the pulsating, fiery heart that gave life to the entire performance. This wasn't just a simple fire, it was a carefully constructed furnace, a contained sun whose intense heat and brilliant light were the sole source of a blacksmith's power. Without the forge, metal remained stubborn, brittle, and useless. With it, the smith could command iron to soften, to flow, to become as pliable as clay in his hands, ready to be transformed by hammer and anvil into any shape he could envision. The forge was the absolute epicenter of the workshop, the focal point around which every tool, every motion, and every ounce of effort revolved. Its glow was the workshop's sun, its heat the very breath of creation. Constructing a forge was the first and most crucial task for any aspiring smith, and its design was a beautiful example of practical engineering using local materials. The most common type was the hearth forge, essentially a contained firebox. Its walls were often built from stones gathered from nearby fields or riverbeds, carefully stacked and mortared together with a special refractory clay that could withstand blistering temperatures without cracking. The floor of this firepot was also lined with clay, shaped into a shallow depression to hold the burning fuel and the metal. The entire structure was usually waist-high, allowing the smith to work for hours without bending over excessively, a vital consideration for both comfort and the precise control required. But forges weren't one size fits all. Their design could vary dramatically based on the smith's specialty. A farrier shoeing horses might use a smaller, portable forge that could be taken to the stable. A swordsmith crafting long blades, however, would need an elongated trench forge, allowing him to heat the entire length of a sword evenly. The forge was the smith's customized command center, perfectly tailored to the work he was destined to perform. The fuel of choice was almost universally charcoal, and for good reason. Unlike wood, which burns with a smoky, inconsistent flame and leaves behind a large amount of ash, charcoal is nearly pure carbon. It burns far hotter and cleaner, providing a more intense and, crucially, more controllable heat. Making charcoal was an industry in itself, done by colliers who slowly burned wood in earth-covered mounds to carbonize it without letting it turn to ash. A smith would source his charcoal carefully, as the size and quality of the pieces could affect how the fire burned. He would build his fire with a core of glowing embers, constantly feeding new charcoal around the edges to maintain a deep, concentrated bed of heat. The real secret, however, lay in managing the fire's atmosphere. A smith would often bury the metal workpieces deep within the fuel, not just lay them on top. This wasn't to hide them. It was to create a reducing environment where the combustion gases from the charcoal would strip oxygen away from the surface of the iron, preventing the rapid formation of scale, that flaky, oxidized layer that eats away at the metal and ruins a good weld. A clean, scale-free heat was the mark of a master fire tender, and then there was the most critical skill of all, one that separated a novice from a master: the ability to read the fire and the metal within it. This was a language of color and light that could not be taught from a book. As the iron heated, it would begin to glow, first a faint, dull red in the shadows of the coals. As the temperature climbed, that red would intensify to a bright cherry, then to a vibrant orange. For most forging work, bending, drawing out, and shaping the ideal color was a bright yellow, almost white heat where the metal becomes as soft as taffy. But for the delicate process of welding, where two pieces of iron are fused together into one, the metal had to reach a near magical state. The smith would watch for a specific, shimmering intensity, often described as the color of a summer sun or a sparkling lemon, when tiny, sparkling flecks would appear on the metal surface like molten dew, a sign that the surface was beginning to melt and was ready to be hammered into a perfect, inseparable bond. Pulling the metal out too early meant a weak, failed weld. Leaving it in a second too long risked burning it, causing the iron to spark and crumble like overdone toast, ruining hours of work. This judgment call, made in the blinding glare of the fire, was the pinnacle of the blacksmith's art, a perfect marriage of empirical knowledge and intuitive feel. The forge, in the end, was more than stone and clay and fire. It was the smith's partner, a living, breathing entity that he learned to converse with, a source of primal power that he learned to harness, transforming earth into iron and iron into the very tools that built a world. Yet for all its contained power, the forge's fiery heart had a critical weakness: it needed to breathe. Without a constant, generous supply of oxygen, even the best charcoal fire would simply smolder, producing a lazy, impotent heat utterly useless for the serious work of moving metal. The bellows were the lungs that solved this problem, the essential partner to the forge that transformed a sleepy bed of embers into a roaring, focused inferno capable of bending iron to human will. This seemingly simple device, often operated by a young apprentice, was the critical link between mere fire and the transformative heat required for true metalworking. Its rhythmic, sighing operation was the steady heartbeat of the smithy, a sound as fundamental to the workshop as the ring of the hammer itself. Constructing a durable set of bellows was a craft in its own right, a perfect fusion of the woodworker's and the leatherworker's arts. The body was typically built from two flat wooden boards, often pine or another softwood for lightness, carefully shaped into elongated ovals or rectangles and hinged together at one end like a giant clamshell book. But the true magic was in the flexible diaphragm that connected them. This was made from a single, tough piece of leather, usually thick, pliable cowhide, which was meticulously stitched and often glued to the wooden boards, creating a completely airtight pouch. A simple but brilliant valve system was the final, critical component. A hole in the bottom board, fitted with a flapped leather valve that opened inward, served as the air intake. On the top board, a metal nozzle or tire was fitted, pointing downward toward the heart of the forge. This tire was the business end, the conduit through which the concentrated blast of air would be delivered. The operation was a study in efficient, rhythmic motion. The apprentice would stand or kneel beside the forge, gripping the handles on the top board. To fill the bellows, he would lift, causing the leather sides to billow out and creating a vacuum that sucked air in through the bottom valve, which would flap open. Then, with a firm, deliberate push, he would collapse the bellows, forcing the captured air out through the tire nozzle and directly into the base of the fire. The leather flap on the intake valve would snap shut under this pressure, ensuring all the air was driven forward. This push-pull rhythm wasn't random, it was a precise skill taught by the master smith. A slow, steady rhythm maintained a consistent heat for general forging, but when the smith needed a welding heat, that brilliant, sparkling temperature required to fuse two pieces of metal, the command would ring out and the apprentice's pace would quicken into a frantic, pumping tempo, driving a torrent of air into the coals to make the fire scream with intensity. The secret to a truly effective bellows, however, lay in its ability to deliver not just air, but a continuous blast. Larger, more advanced forges often employed a double-chambered bellows system to solve the problem of the pause between strokes. These consisted of two sets of bellows mounted side by side and operated by a single lever, cleverly timed so that while one chamber was being lifted to fill with air, the other was being compressed to deliver its blast. This ingenious setup created a nearly uninterrupted stream of air, allowing the fire to maintain a remarkably stable and intense heat, a crucial advancement for smelting ore or working with larger pieces of steel. The size of the bellows also mattered immensely. A small, handheld pair might be used by a jeweler for delicate work, while the bellows for a castle's armory could be massive, requiring a dedicated operator and perhaps even a water wheel or treadmill for power. This control over airflow was what gave the medieval blacksmith his true command over temperature, the most critical variable in his work. By directing the tire's blast, he could create a small, super hot spot within the larger fire, perfect for heating only the tip of a tool or the tang of a blade. He could make the fire broad and less intense for annealing, softening metal to relieve stress. The bellows were the throttle and the smith was the pilot. This ability to precisely manage heat is what enabled the creation of everything from the finely tempered steel of a warrior's sword to the durable, shock-resistant iron of a farmer's plowshare. It was the breath of life for the forge, the invisible force that turned a simple fire into the most important tool in the medieval world, empowering the smith to perform his alchemy and shape the very bones of civilization. Yet for all the rhythmic pounding of the forge and the methodical construction of joints, another kind of rhythm was essential to medieval life, one that was quieter but no less vital. This was the steady, whirring hum of the treadle wheel, a tool that transformed the tedious, hand-cramping work of spinning into a faster, more efficient process that literally fueled the entire textile economy. To understand its revolutionary impact, we have to look at what came before it, the simple drop spindle. For millennia, spinners, overwhelmingly women, had to manage every aspect of the process by hand. They would hold a bundle of prepared fibers called a distaff under one arm, and with the other hand, they would constantly twirl a weighted spindle suspended in the air, gently feeding out fibers to be twisted into thread. It was portable, yes, but it was incredibly slow and required the spinner's constant, undivided attention. The treadle wheel changed this dynamic entirely by introducing one brilliant innovation: foot power. The mechanics of the wheel were an elegant solution to a complex problem. At its heart was a large, hand-turned wheel connected by a drive band to a much smaller spindle. The key breakthrough was the addition of a foot pedal or treadle, linked to a crankshaft that converted the up and down motion of the foot into a smooth, continuous rotation of the large wheel. This single development was transformative. For the first time, the spinner's hands were completely liberated. One hand could now focus solely on holding and drafting the fibers from the distaff, controlling the thickness and consistency of the thread, while the other hand guided the newly spun thread onto the spindle. This division of labor between hands and foot allowed for a dramatic increase in both speed and the quality of the thread produced. The spinner could now achieve a much more consistent twist, creating stronger, finer, and more uniform yarns that were essential for producing higher quality cloths, especially the finer worsted wools and linens that were increasingly in demand. Mastering this new tool, however, was less about brute strength and more about developing a perfect, unconscious rhythm, a delicate dance between limb and material. The secret to a master spinner's success was in the seamless coordination of her foot on the treadle and her fingers as they drafted the fibers. The foot had to maintain a steady, even pace. Too fast, and the thread would over-twist, becoming kinky and brittle. Too slow, and the thread would be weak and underspun, prone to breaking. Meanwhile, the fingers had to draft or pull the fibers out at exactly the same rate the spindle was twisting them, a skill that required an intuitive feel for the character of the wool or flax. Different fibers demanded different rhythms. Short, sticky wool might need a slower, more deliberate draft, while long, sleek flax fibers could be drawn out more quickly. This nuanced knowledge was the spinner's art, a deeply ingrained muscle memory learned through years of practice, often starting in childhood at her mother's or grandmother's side. The gentle, rhythmic thumping of the treadle became the soundtrack of the medieval home, a sound of productive, skilled labor. The construction of the wheel itself was a testament to local craftsmanship. While the metal fittings, the axle, crankshaft, and hooks were the work of the blacksmith, the wheel's body was almost always crafted by the village carpenter or wheelwright. It was built from strong, seasoned hardwoods like oak or beech for the frame and spindle, and a lighter wood-like poplar for the large wheel itself to ensure it could be turned easily. These wheels were not mass-produced. Each one was made to order, often adjusted to fit the height and posture of the specific spinner who would use it. This customization was crucial for comfort during the long hours spent at the wheel. The simplicity of its mechanism, wood, cord, and a little ingenuity meant that it could be built and repaired in any village, making the technology accessible and widespread. This democratization of a more efficient tool meant that households could produce far more thread than they needed for themselves, creating a surplus that could be sold or woven into cloth for market, weaving the individual spinner directly into the vast and profitable tapestry of medieval trade. While the treadle wheel spun its rhythmic magic inside the home, outside, medieval builders were engaged in a far more monumental task, one that demanded a different kind of precision, not of thread but of line and plane. Amidst the cacophony of hammers and chisels, the success of their endeavors, the very stability of their creations, hinged on a deceptively simple question: is it level? In a world without laser guides or digital readouts, ensuring a surface was perfectly horizontal was a fundamental challenge that could mean the difference between a cathedral that touched the heavens for centuries and a barn that collapsed under the first heavy snow. The medieval builder's solution to this problem was a tool of elegant simplicity and profound importance: the level. Though primitive by our standards, its invention and use represent a critical leap in applied mathematics and practical physics, a testament to the medieval mind's growing desire to impose perfect order on an imperfect world. The most common and versatile level was the water level, a tool whose principle was so flawless it is still used by some masons today. Its design was brilliantly uncomplicated: a long, narrow trough of wood, often shaped like an elongated U-channel, open at the top and filled with water. The fundamental law of physics it relied upon is that water, when undisturbed, will always seek its own level. A builder would place this trough on a surface he wished to check. He would then wait for the water to become perfectly still. By observing the water's surface at both ends of the trough relative to a mark on the wood, he could determine with remarkable accuracy if the surface beneath was truly horizontal. For longer distances, such as establishing a level foundation around the entire perimeter of a large building, two builders would use a longer version of this tool, or even a simple length of clear hose filled with water, each watching the water line at their respective end and calling out adjustments until the liquid at both ends settled at exactly the same height. This method was incredibly effective over long spans and was essential for projects like the Great Aqueducts and the foundational courses of castle walls, where a mistake of even an inch over 100 feet could lead to catastrophic failure. For work that required a more immediate one-person reference, builders turned to another ancient tool, the plumb bob level. This device typically consisted of a straight, wooden frame with a horizontal crossbar. From the apex of the a braided cord with a heavy, pointed metal weight, the plumb bob was suspended. The secret to its operation lay in a carefully scribed mark on the crossbar directly below the suspension point. When the feet of the frame were placed on a surface, the builder would simply watch the hanging plumb line. If the surface was perfectly level, the cord would hang directly over that central mark. If it was off, the cord would swing to one side, visually indicating which way the surface needed to be adjusted. The plumb bob itself was a masterpiece of the blacksmith's art, forged from lead or bronze into a perfectly symmetrical, heavy teardrop shape to ensure it would hang straight and true without swaying excessively. The pointed tip allowed for a precise reading against the mark, but the true secret to the accuracy of any medieval level wasn't just in its construction. It was in the careful calibration and, most importantly, the experienced eye of the master builder. A level was only as good as its initial setup. A water trough had to have a perfectly straight top edge. If the wood was warped or uneven, the entire measurement would be compromised. A plumb bob frame had to be assembled with absolute precision, ensuring the crossbar was perfectly parallel to the base and the suspension point was centered exactly. This initial calibration was a painstaking process, often checked against a known true surface like a still pond. Once calibrated, the tool was treated with immense care, a prized possession in a master's toolkit. Furthermore, the builder had to know how to interpret the results. On a windy day, a plumb bob might sway, requiring patience to find its true resting point. On a building site with constant vibration, the water in a level might never become perfectly still, demanding the builder's judgment to estimate its average position. This is where years of experience came into play, an intuitive feel for the materials and the environment that no tool could ever provide. This relentless pursuit of the level and the plumb line, the true horizontal and the true vertical, was the invisible geometry behind every enduring medieval structure. It was the reason the foundations of Romanesque churches were so stable, the reason the floors of great halls were even and true, and the reason the arches of bridges could bear their immense loads symmetrically. When we look up at the soaring vaults of a Gothic cathedral, we marvel at the height and the light, but we should also marvel at the profound levelness of the floors we stand on and the perfect verticality of the pillars that rise around us. These were not happy accidents, they were the hard-won results of simple tools wielded with sophisticated understanding. The humble level, in its watery or weighted form, was a direct physical manifestation of humanity's grasp of natural law, a tool that allowed abstract concepts of geometry and physics to be translated into stone and mortar, ensuring that what they built would not only rise but would stand the test of time. While the level ensured the grand lines of a building were true, it was another, far more intimate tool that gave those structures their soul and their story, the chisel. This was the instrument of fine detail, the conductor's baton that directed the final, defining movements in the symphony of construction and art. In the hands of a master, a chisel was not merely a cutting tool. It was a paintbrush, a pen, a magician's wand that could coax intricate foliage from cold stone or transform a solid oak beam into a gallery of carved saints and mythical beasts. Its versatility was its greatest strength, serving equally the carpenter framing a roof, the mason dressing a block for a cathedral wall, and the sculptor capturing a moment of divine grace for all eternity. From the roughest preliminary work to the most delicate finishing touch, the chisel was the key that unlocked the beauty hidden within the material. The fundamental design was beautifully simple: a hardened steel blade with a sharpened edge at one end and a striking surface or butt at the other. But this simplicity belied a universe of specialized forms, each one a custom-keyed solution for a specific lock. A carpenter's firmer chisel, with its stout, rectangular blade, was built for strength, driven by a wooden mallet to chop out deep mortises or pare away large sections of wood. Just a few feet away, a mason would be wielding a completely different tool, a hefty bolster chisel with a wide, flat blade and a beefy head designed to be struck with a heavy iron hammer, capable of shearing off great chunks of limestone or granite to rough out a shape. And then there were the specialists for fine work, the cabinet makers. Paring chisels with long, elegant blades and sharp bevels were never struck at all. They were carefully pushed by hand for shaving away paper-thin slivers of wood to achieve a perfect fit. The sculptor's tools ran the entire gamut, from massive points for initial blocking to tiny veiners and dogleg chisels that could carve the delicate eyelid of a statue or the veining on a marble leaf. The true secret to a chisel's phenomenal effectiveness, however, lay in two critically important factors that were the closely guarded knowledge of both the blacksmith who forged it and the artisan who used it: the quality of the steel and the geometry of the edge. Not all iron was created equal. A master smith knew how to weld a thin strip of high-carbon steel capable of being hardened to a razor's edge to a tougher, more flexible iron body that could absorb the shock of repeated hammer blows without snapping. This process, called pattern welding, created a blade that was both hard and tough, a perfect marriage of properties. Once forged, the magic was in the heat treatment. Heating the steel to a critical temperature and then quenching it rapidly in water or oil would make it incredibly hard but also dangerously brittle. The final, essential step was tempering, gently reheating the blade to a specific, lower temperature to draw back just a little of that hardness and introduce a measure of flexibility. A master smith would often judge this temperature by the color of the oxide film that formed on the polished steel: a pale straw yellow for a razor-sharp carving chisel, a beautiful peacock blue for a mason's heavier duty tool that needed more shock resistance. This delicate balance was the difference between a tool that held its edge through a day's work and one that shattered on the first strike, and it was a knowledge earned through decades of experience. Then came the sharpening, a ritual as important as the forging itself. The angle of the bevel ground onto the cutting edge was not arbitrary. It was a precise calculation based on the material and the task. A steeper, more robust bevel was used for hardwoods and stone, providing strength behind the edge to prevent chipping. A shallower, more acute bevel was reserved for softwoods and fine paring, allowing the blade to slice through the material with minimal resistance. Maintaining this perfect edge was a daily discipline for the artisan. He would hone his chisels on a series of progressively finer sharpening stones, often imported from quarries in Belgium or Turkey, until the edge was so sharp it could split a free hanging hair. This wasn't vanity, it was practicality. A sharp chisel required less force to use, was easier to control for precise cuts, and left a cleaner, smoother surface that often needed no further sanding. A dull chisel was dangerous, requiring more force and being more likely to slip and cause injury or ruin the workpiece. And so, armed with this array of perfectly tuned instruments, the medieval artisan set to work, and the world they created still takes our breath away. The chisel was the tool that gave us the soaring verticality of Gothic architecture, its countless thousands of individually carved stones, all precisely dressed to fit together in a perfect, soaring puzzle. It is responsible for the breathtaking detail of the wooden choir stalls in great cathedrals, where each misericord tells a different story from scripture or daily life, all executed with a clarity and vitality that makes the wood seem alive. It carved the stone gargoyles that stare down from the rain spouts, the intricate tracery of rose windows, and the delicate linen fold patterns on noblemen's chests. Every stroke of the mallet, every precise chip removed, was a decision made by a human hand and eye. The chisel's legacy is therefore a deeply human one. It left behind not just objects of beauty, but the undeniable evidence of individual skill and artistic vision, the unique mark of a craftsman who, centuries ago, trusted his skill, his tools, and his eye to leave a permanent record of his time on earth, one precise, intentional chip at a time. While the chisel and the adze were masters of shaping and carving, another tool was the undisputed champion of division, the saw. This was the instrument of separation, the tool that could take a massive, unwieldy log and, with a relentless back and forth motion, tame it into manageable planks, beams, and boards. But the medieval saw was far more than a simple serrated blade. It was a sophisticated family of tools, each member designed for a specific and vital task in the transformation of timber. From the rough, aggressive rip saw that could split a tree trunk along its grain to the delicate, fine-toothed tenon saw used for the most precise joinery, this tool brought a new level of efficiency and accuracy to the woodworker's craft, fundamentally changing the speed and scale of what could be built. The earliest and most straightforward saws were simple hand saws, essentially a long, tapered blade of iron with teeth cut into one edge, fastened to a wooden handle. These were the workhorses for rough dimensioning, for cutting logs to length or for ripping them into planks, but their design had a major limitation. The blade was relatively thin and flexible, and it was difficult to keep it perfectly straight in a long cut, especially in tough green wood. The brilliant innovation that solved this problem was the frame saw or bow saw. This design mounted a narrow, flexible blade within a tall, H-shaped wooden frame, with the blade held under tension by a twisted cord or a toggle stick. This tensioning system was the secret to its success. By tightening the cord, the woodworker could pull the blade taut as a bowstring, eliminating any flex and ensuring it would track perfectly straight through even the most resistant timber. The frame itself also provided a built-in guide for the cut, allowing for far greater control and precision. This design was so effective that variations of it are still used by traditional woodworkers today. However, the true heart and soul of any saw, the element that defined its character and capability, was not in its frame but in its teeth. To the untrained eye, a saw's teeth might look like a simple, repetitive pattern, but to a medieval carpenter, they were a complex language of angles, sets, and spacing, each combination meticulously designed for a specific type of cut. The first critical distinction was between rip teeth and crosscut teeth. A rip saw designed to cut with the wood grain had teeth filed straight across, acting like a series of tiny chisels that would scrape and gouge their way along the fiber's length. A crosscut saw, meant to cut across the grain, had teeth filed to a sharp point, each one acting like a miniature knife that would score and sever the wood fibers cleanly. Using the wrong tooth pattern for the job would result in a brutally difficult, ragged cut that looked like it had been chewed through by a wild animal. Beyond the tooth shape was the concept of set. This referred to the way the teeth were deliberately bent or set, alternating slightly to the left and right away from the plane of the blade. This was the saw's second great secret. Without set, the blade's body would rub against the sides of the cut, creating immense friction and binding almost immediately. The set created a curve, the path of the cut, that was slightly wider than the blade itself, allowing it to move freely without getting stuck. The amount of set was crucial. Too little, and the saw would bind and overheat. Too much, and the cut would be wasteful and require far more physical effort to push the saw through the wood. Finally, the spacing of the teeth, known as the points per inch, determined the saw's aggression and the smoothness of the finish. A saw with large, widely spaced teeth would remove material quickly but leave a rough surface, perfect for initial breakdown of logs. A saw with fine, closely spaced teeth would cut more slowly but leave an almost glassy, smooth surface, ideal for the final cuts on a piece of fine furniture where the joint would be visible. Forging and sharpening a saw blade was a specialized blacksmithing art that demanded immense patience and a steady hand. The smith would first forge a long, thin strip of good quality iron, often welding a harder steel edge to it to ensure the teeth would hold their sharpness. Then, using a small, triangular file, he would painstakingly cut each individual tooth into the blade's edge. This was not a haphazard process. He would use a wooden block with evenly spaced notches as a guide to ensure every tooth was perfectly uniform in its size and spacing. After the teeth were cut, he would then perform the set, using a special tool called a saw rest to gently bend each tooth to its precise angle. The final act was the sharpening, again done with that same triangular file, carefully running it along the edge to put a razor edge on every single tooth. A well-maintained saw was a prized and valuable possession, often bearing the maker's mark and cared for with obsessive attention to prevent the dreaded enemy of all saws, rust. The impact of the saw on medieval construction is almost impossible to overstate. Before its widespread use, wood was primarily shaped by splitting it along the grain with axes and wedges, a process that was wasteful and limited the shapes that could be made. The saw changed this dynamic completely. It allowed for the efficient conversion of whole logs into standardized planks and squared timbers, which in turn revolutionized building techniques. The classic timber-framed buildings that characterize medieval towns, with their intricate webs of exposed beams, were made possible by the saw's ability to produce consistently sized members. It was essential in shipbuilding for cutting the long, curved planks needed for hulls. It allowed furniture makers to create thinner, more elegant panels for chests and doors. By drastically reducing the labor required to dimension wood, the saw didn't just make the work faster. It expanded the very imagination of what was possible to build, enabling the complex wooden skeletons that supported the medieval world, one precise, efficient stroke at a time. But if the anvil was the unyielding stage and the forge the blazing heart, then the hammer was the blacksmith's own will made manifest the extension of his arm, the focus of his strength, and the instrument of his intent. In the percussive symphony of the smithy, every other sound was merely accompaniment to the lead performer, the clear, sharp ring of hammer on hot metal. This was not a single monolithic tool, but a diverse family of instruments, each one a specialist in a specific aspect of the transformative dance between force and form. A master smith's collection was his personal orchestra, and knowing which hammer to pick up was the first note in composing a new object from raw, shapeless iron. The most iconic of these was the cross-peen hammer, instantly recognizable by its distinctive head. One side featured the standard flat face for general striking and flattening, but the other tapered into a narrow, rounded wedge called the peen. This unique shape was the secret to its incredible versatility. When a smith needed to draw out a piece of metal, to lengthen and thin it, say, for creating a long, tapered point or flattening a bar into a blade, the cross-peen was his go-to tool. He would use the flat face for the initial heavy blows to set the direction, but then he would turn the hammer and use the edge of the peen. By striking at an angle and focusing the immense force into a narrow line, the peen would stretch the hot metal laterally, spreading it out like warm butter with an efficiency a flat face could never achieve. It was a perfect demonstration of physics in action, concentrating energy to move material in a very specific, controlled way. For work requiring a more rounded form, the ball-peen hammer took center stage. As its name suggests, one side of its head was a hemisphere of polished steel. This spherical peen was the essential tool for the delicate art of peening or planishing, the process of smoothing and hardening a metal surface by working it with a rounded tool. It was indispensable for shaping and strengthening the rounded crowns of helmets or the bowls of ladles, but perhaps its most critical function was in the creation of rivets. After the hot rivet was inserted through two pieces of metal, the smith would use the flat face of the ball peen to hold the rivet steady on the anvil, while an apprentice would use the ball end to carefully mushroom the other side of the hot rivet head, flaring it out to create a permanent, incredibly strong mechanical bond that held everything from armor plates to wrought iron gates together. For centuries, yet the true magic of any hammer lay not in its shape alone, but in its intimate relationship with the smith who wielded it. The weight and balance of a hammer were deeply personal choices, fine-tuned to the individual's strength and style. A hammer that was too heavy would quickly exhaust the user and sacrifice precision for power. One that was too light would fail to move the metal effectively, requiring far more strikes and wasting precious heat. The ideal weight was a perfect compromise, allowing for a smooth, fluid swing that generated maximum force with minimal effort. The handle or haft was just as important. It was almost always crafted from a tough, shock-absorbent wood like hickory or ash, chosen for its ability to withstand thousands of impacts without splintering. The smith would personally shape the handle to fit his grip perfectly, often thinning it in the middle for a secure hold and leaving it thicker at the end to act as a counterweight, improving the overall balance. A well-made hammer felt like an extension of the arm, not a separate tool. And then there was the technique, the secret knowledge passed from master to apprentice through careful observation and countless hours of practice. It was never about brute force. A novice would swing from the shoulder, putting all his might into a wild, inaccurate blow that wasted energy and often missed its mark. A master, however, knew that true power came from the wrist and the elbow, generating a controlled, whip-like action that delivered the head of the hammer to the metal with pinpoint accuracy and stunning force. He understood the rhythm of the strike, the precise moment to lift the hammer for the next blow to allow the metal a fraction of a second to relax under the impact. He knew exactly which part of the hammer's face to use, the center for a solid, direct blow or the edge for a shearing cut. Most importantly, he knew how to listen to the hammer. The sound of a strike told him everything about the temperature and condition of the metal beneath it. A dull thud meant the metal was too cold and needed to go back into the fire. A clear, ringing ping meant it was at the perfect heat for forging. A master blacksmith didn't just hit metal, he conversed with it, and the hammer was his voice. In its rhythmic, purposeful blows, we hear the very sound of creation itself, the relentless, determined pulse that turned a lump of ore into a nail, a hinge, a sword, or a plowshare, the essential objects that built, fed, and defended the medieval world. Yet for all the percussive force of the hammer and the precise cuts of the saw, another tool harnessed a completely different kind of energy, the smooth, continuous momentum of rotation. In a quiet corner of the medieval workshop, away from the forge's roar, the potter engaged in a more subtle but equally vital form of creation at the pottery wheel. This was not merely a tool for making dishes. It was a machine that captured the very essence of circular motion, transforming a lump of inert clay into a perfect, symmetrical vessel with a grace and speed that hand building could never match. The potter's wheel was a bridge between the raw earth and the refined object, a device that turned simple mud into the containers that held a society's food, drink, and trade goods, making it one of the most indispensable technologies for daily life. The design of the medieval kick wheel was a marvel of straightforward, effective mechanics. At its heart was a heavy, flat stone or a thick wooden disc mounted on a vertical axle. This was the flywheel, the secret to the entire system's operation. The potter would set a lump of clay on a smaller head, or wheel head, attached to the top of the axle, and then use their foot to spin the large, heavy flywheel below the bench. The mass of that lower wheel was the key. Once set in motion, its inertia kept it spinning smoothly and consistently, allowing the potter to use both hands freely to shape the clay without interruption. This foot-powered operation was a significant advancement over earlier slow-turning wheels that required an assistant to keep them moving, liberating the potter to work alone and achieve a much more intimate connection with the spinning clay. The entire assembly was often sunk into a pit in the workshop floor, positioning the flywheel at the perfect height for a rhythmic, comfortable kicking motion that could be maintained for hours. But the real magic, the true art that separated a master potter from a novice, happened in the first few seconds of contact with the spinning wheel. This was the critical act of centering, a skill that looks deceptively simple but is perhaps the most difficult to master in all of pottery. The potter would slam the wet clay down onto the center of the wheel head and then start the flywheel spinning. As the lump whirled around, the potter would wet their hands and apply steady, immense pressure, forcing the clay to conform to the perfect axis of rotation. An uncentered lump would wobble violently, refusing to yield to the potter's touch and making it impossible to form a symmetrical pot. Achieving perfect centering required a deep, intuitive feel for the clay's consistency and the wheel's speed, applying just enough pressure to coax the clay into submission without distorting it or causing it to collapse. It was a physical dialogue between the potter's hands and the spinning earth, a test of strength, patience, and sensitivity that was the absolute foundation of all that followed. Once centered, the transformation was almost alchemical. The potter would press their thumbs into the center of the spinning mound, opening up a cavity. With one hand inside the pot and the other outside, they would then draw the walls upward, the clay responding to the slightest pressure by stretching and thinning. The control of speed was paramount here. A slower rotation was used for opening and for shaping larger, more delicate forms, allowing for careful, deliberate movements. A faster spin was employed for finishing, for refining the rim, or for throwing smaller, more intricate pieces. The potter's hands were never still. They were constantly sensing the thickness of the wall, guiding the shape, and using the centrifugal force of the wheel itself to help spread the clay into a perfect, balanced form. A master potter could throw a dozen nearly identical jugs in an hour, a consistency and efficiency that was crucial for meeting the demands of a household or a marketplace. The process didn't end when the pot was thrown. While still on the wheel, the potter would use a variety of simple tools to add the final touches. A piece of leather or a smooth wooden rib would be pressed against the surface to compress the clay particles and smooth away imperfections, strengthening the vessel and giving it a refined finish. A loop of wire, deftly slipped under the base, would sever the finished pot from the wheel head with a clean cut. Then came the firing, the final transformation in a wood-burning kiln that permanently hardened the clay through chemical change, making it capable of holding liquid and surviving daily use. The pottery wheel, therefore, was more than just a shaping tool. It was the core of an entire craft that blended brute physicality with delicate artistry, turning the most humble material on earth into objects of both absolute necessity and surprising beauty. But while the potter used the wheel's rotation to build vessels from the inside out, another tool performed a far more focused and penetrating task, creating the essential voids that allowed separate pieces to become one. In a world bound by sinew, wood, and leather, the ability to make a clean, precise whole was a fundamental act of assembly, and for this, the master craftsman turned to the awl. This was a tool of breathtaking simplicity and unwavering purpose, a sharp, hardened steel point mounted firmly in a handle, designed to do one thing perfectly: pierce. It required no complex mechanism, no great strength, but it demanded a steady hand, a keen eye, and an intimate understanding of the material being worked. In the hands of a cobbler, a bookbinder, or a carpenter, this humble spike was the key that unlocked the next stage of creation, transforming prepared parts into finished, functional goods. The design was a perfect study in focused force. The business end was a spike, typically square or diamond shaped in cross-section, tapering to a needle-sharp point. This geometric choice was the first secret to its effectiveness. A round awl would simply push material aside, stretching and often tearing the fibers of leather or wood, leaving a ragged, weak hole that might close up. The sharp edges of a square or diamond sectioned awl, however, actually cut the fibers as it was pressed through, shearing them cleanly and leaving a precise, slit-like hole that was perfect for receiving a needle or a peg. This hole would maintain its shape and strength, a critical feature for something like a shoe that would be constantly flexing or a book that would be opened and closed for generations. The awl was never meant to remove material like a drill. Its purpose was to part it to create a clean opening without loss. This precision placed the tool's performance squarely in the hands of the blacksmith who forged it. Creating a perfect awl was a test of a smith's skill in heat treatment. The entire point had to be made from high-carbon steel, heated and quenched to achieve a glass-hard state that could be honed to a terrifyingly sharp tip. But this hardness came with a price: brittleness. If the entire spike were that hard, the first misaligned push could snap the point clean off. The solution was a sophisticated forging technique where the smith would only harden the very tip and the cutting edges, leaving the body of the spike and the tang, the part that went into the handle, softer and more flexible. This created a tool that was both razor-sharp at its point and tough enough to withstand lateral pressure without breaking, a delicate balance that was the hallmark of a masterfully made tool. The handle, often crafted by the very artisan who would use it, was equally important. It was typically made from a dense, hard-wearing wood like boxwood or fruitwood, shaped and sanded to fit the user's hand perfectly. For a cobbler who might use an awl for hours on end, the handle's comfort and grip were essential to prevent fatigue and maintain control. Some featured a flared end or a rounded pommel designed to fit snugly in the palm, allowing the user to apply steady, firm pressure with their whole arm, not just their fingers. The tang of the awl was driven deep into the handle and often secured with a small metal ferrule to prevent the wood from splitting under repeated force. This marriage of a perfectly tempered steel point and a custom-fitted handle made the awl a deeply personal and trusted implement. Watching a master use an awl was to witness a lesson in controlled application. The process was nothing like the frantic drilling of a modern power tool. It was slow, deliberate, and meditative. A bookbinder, for instance, would have a stack of folded parchment pages, a cover, and a length of cord ready. Using a ruler and a stylus, he would first mark the exact positions for the holes that would hold the binding. Then, with the stack firmly clamped, he would take his awl and with a firm, steady, twisting pressure, push it through the entire thickness. The twist was crucial. It helped the cutting edges do their work and ensured the hole was clean through every layer. A single clumsy push could misalign the entire book. For a cobbler stitching a sole to an upper, the awl would precede the needle, punching the holes through the tough leather that the bristle-loaded needle would then follow. The rhythm was hypnotic. Punch a hole, set the awl down, take the needle and pull the stitch through, then pick up the awl again for the next hole. This was the rhythm that built durability, one perfectly placed hole at a time. The awl's legacy is woven into the very fabric of medieval daily life, though it is often invisible in the finished object. Every sturdy leather boot that protected a traveler's feet from the mud and stones of a medieval road began with the push of an awl. Every functional horse harness that allowed a farmer to plow his field or a knight to control his charger in battle relied on the precise holes punched through thick straps to hold buckles and rings. And perhaps most beautifully, every illuminated manuscript that preserved knowledge, scripture, and art for posterity was literally held together by the work of this simple tool. The awl didn't create the gorgeous illuminations or the careful script, but it made the physical book itself possible, its tiny, neat holes guiding the linen thread that bound the pages through centuries of use. In its quiet, piercing action, we find a profound truth of medieval craftsmanship. that grand achievements and enduring objects are often built upon a foundation of countless perfect, simple actions. The awl didn't demand glory, but it guaranteed integrity, proving that the smallest, sharpest point could be the crucial link in the chain of creation. While the blacksmith's hammer shaped metal and the potter's wheel shaped clay, out in the sun-drenched fields, another tool was shaping the very livelihood of medieval society, the scythe. This iconic instrument, with its long, gracefully curved blade and elegantly angled handle, represented a quantum leap in agricultural efficiency. To understand its revolutionary impact, we have to consider the back-breaking alternative, the sickle. With a short, hooked blade, the sickle forced the harvester to stoop low and cut each individual stalk of grain one handful at a time, a painfully slow and exhausting process that left the worker bent double for hours under the hot sun. The scythe changed all of that. Its genius was in its ergonomics and its physics, allowing the user to stand upright and, with a smooth, swinging motion, cut a wide, clean swath through the crop with every pass. This wasn't just an improvement, it was a complete reimagining of the harvest, turning a task of grueling endurance into one of powerful, rhythmic efficiency. The secret to this transformative power lay in the sophisticated interplay between its components, each one carefully engineered for a specific purpose. The blade itself, or the blade, was a long, thin crescent of steel, sharpened along its entire inner curve. This curvature was the first critical innovation. As the blade was swung in a low, horizontal arc, the curve ensured that the sharpened edge made contact with the stalks at a perfect slicing angle, severing them cleanly rather than just smashing through them. But the blade didn't work alone. Mounted at a near-perfect right angle to the main handle, or snathe, was a set of two smaller, auxiliary handles called nibs. These allowed the user to guide and control the blade with both hands, distributing the effort across the entire body and providing the leverage needed to maintain that smooth, sweeping motion. The final, often overlooked component was the blade ring, a simple twisted metal loop that attached the blade to the snathe. This ring was designed with a degree of flexibility, acting as a shock absorber that took the brunt of the impact when the blade occasionally hit a hidden rock or a tough patch of earth, protecting both the precious blade and the user's wrists and arms from jolting vibrations. However, the true art of the scythe was not just in its construction, but in its use. Wielding one effectively was a skill that combined strength, rhythm, and an almost intuitive feel for the tool. A master harvester didn't simply hack at the grain. He performed a fluid, dance-like motion. He would plant his back foot, set his stance, and then initiate a swing that started in his core and torso, transferring that rotational energy through his arms and into the blade, which would whistle through the air and slice through the stalks at ankle height. The follow-through was just as important, allowing the momentum to carry the cut grain to the side in a neat windrow, ready to be gathered and bound into sheaves. The rhythm was everything: a steady, metronomic swing steps, wing that could be maintained for hours, a rhythm that became the soundtrack to the harvest season. A novice would quickly tire himself out with short, choppy, inefficient strokes, but an experienced user could clear an astonishing amount of ground in a day, his movements looking less like labor and more like a well-practiced performance. This performance, however, relied on a tool that was kept in peak condition, and that responsibility fell to the blacksmith and the user in equal measure. The smith's role was to forge a blade that was both tough and capable of holding a fearsomely sharp edge. The best scythe blades were composite creations. The body was made from a softer, more flexible iron that could withstand the shocks and bumps of fieldwork without cracking. The cutting edge, however, was a thin strip of high-carbon steel forge welded onto that iron body. This steel could be hardened and honed to a razor's edge that would glide through fibrous stalks with minimal resistance. But even the finest steel edge would dull quickly against silica-rich cereal grasses. This is where the harvester's own maintenance kit came into play. He carried a whetstone in a leather holster filled with water on his belt. Every few minutes, he would stop his swing, briefly touch up the edge with a few practiced strokes of the stone, a process called whetting to restore its lethal sharpness. This constant, rhythmic cycle of cutting and sharpening was the heartbeat of the harvest, a small pause that ensured immense productivity. The scythe's impact on medieval society, therefore, extended far beyond the field. By dramatically speeding up the harvest, it reduced the window of vulnerability when a sudden rainstorm could flatten a crop or ruin cut grain before it could be gathered. This increased reliability in bringing in the harvest was a cornerstone of food security, supporting population growth and stability. It also changed the social dynamics of the harvest itself. While still immensely demanding work, the scythe's efficiency meant that a village could bring in its crops with slightly fewer laborers, or could harvest larger areas, generating surplus grain that could be stored or sold. The tool became so central to rural life that it transcended its function, evolving into a powerful symbol. It featured in folk tales and art, representing both the relentless labor of the peasantry and the fruitful abundance of the land. In the scythe's long, sweeping arc, we see the culmination of centuries of agricultural ingenuity, a perfect marriage of form, function, and human skill that turned the annual race against time into a manageable and even graceful dance of survival. Yet for all the grandeur of the scythe sweeping through fields of grain, the most essential cutting tool in the medieval world was one of breathtaking intimacy and personal connection, the Whittle-Tang knife. This was not a tool kept in a workshop or wielded for a single seasonal task. It was a constant companion, an extension of the individual's own hand, carried on the belt from childhood to old age. In an era before disposable cutlery or specialized gadgets, this single, versatile blade was the Swiss Army knife of its day, a masterclass in minimalist design that was called upon to perform a staggering array of daily duties. From the nobleman's table to the woodcarver's bench, from the farmer's field to the housewife's kitchen, the Whittle-Tang knife was the undisputed champion of everyday utility, a testament to the principle that the best tools are often the simplest, and the most used are the most personal. The name itself, Whittle-Tang, reveals the elegant secret of its construction and its inherent strength. Unlike a full tang knife, where the metal of the blade extends all the way through the handle, the Whittle-Tang was a study in efficient use of precious materials. The blacksmith would forge the blade, and then, while the iron was still hot and malleable, he would draw out the metal at the base into a narrow, pointed spike, the tang itself. This spike was significantly thinner than the blade, designed to be driven directly into a solid block of wood, antler, or bone that served as the handle. The term whittle comes from the process of whittling or carving the handle material to fit the user's grip perfectly around this central spike. This design was incredibly strong for its intended purposes, as the force applied to the blade was transferred in a straight line down the length of the tang, which was securely locked inside the handle by friction, glue, and sometimes a single, small metal pin. It was a lighter, less resource-intensive way to make a knife, but it demanded absolute precision from both the smith and the user who fitted the handle. The true measure of a knife's quality, however, was not in its tang but in its soul, the temper of its blade. This was the blacksmith's closely guarded art, a delicate alchemical dance between fire, water, and steel. A blade that was too soft would dull almost immediately, its edge rolling over at the first encounter with a tough piece of bread crust or a branch of green wood. A blade that was too hard, however, was even worse. It would be brittle as glass, prone to chipping or even snapping catastrophically under pressure. The secret was to find the perfect balance. The smith would heat the finished blade to a specific critical temperature, judged by the color of the glowing steel, a bright cherry red. He would then quench it rapidly in water or oil, instantly freezing the steel's crystalline structure into an extremely hard but dangerously brittle state. The final, crucial step was tempering, gently reheating the blade to a much lower temperature to relieve some of that internal stress. He would watch the surface of the metal as it warmed, waiting for it to blush with a specific color, a pale, straw yellow for a razor-sharp carving knife that needed to hold a fine edge, a beautiful deep blue for a more robust general-purpose blade that could withstand occasional prying or shock. This final color was the signature of a master smith, the invisible quality that turned a piece of sharpened metal into a trusted, lifelong tool. Once the smith had done his work, the knife was handed over to its owner, and the final act of its creation began, the fitting of the handle. This was where the tool truly became personal. The handle material was chosen not just for durability, but for feel and even status. Common folk might use a sturdy, locally sourced wood like birch or oak, carved to fit the grooves of their own palm. A more prosperous farmer might use a piece of antler, its natural curve fitting snugly in the hand and its porous core providing a superb grip, even when wet. A wealthy merchant or noble might have a handle of polished bone or even exotic imported wood, inlaid with brass. The process of fitting was a careful one. The chosen material would be drilled with a narrow hole, slightly smaller than the tang itself. The tang would then be heated often by simply holding it over a candle flame, and then slowly, carefully driven into the handle. The heat would slightly char the wood or expand the antler, creating an incredibly tight, permanent bond as it cooled and contracted. The handle would then be whittled and sanded to a perfect custom fit. This meant that no two knives were exactly alike. Each one was a unique collaboration between the smith's skill and the owner's own hand, a physical record of their grip and their needs. And from that moment on, the knife was never far from its owner's side. Its uses were as endless as the demands of daily life. At mealtimes, it was the primary eating utensil for everyone at the table, used to spear meat from a communal pot, slice bread, and spread cheese. In the kitchen, it was the original chef's knife, used for chopping vegetables, boning fish, and preparing herbs. For the craftsman, it was a precision instrument. A woodcarver would use it for everything from roughing out a shape to putting the finest details on a figurine. A leather worker would use it to cut and trim hides. A scribe might use a small, delicate version to sharpen his quills and scrape errors from parchment. For the peasant farmer, it was a tool for 100 small tasks, cutting a new button from a piece of horn, trimming a wick for a candle, sharpening a stake, or even performing minor repairs on harnesses and gear. It was the first tool reached for in any situation, the default solution to 1,000 small problems. This constant, intimate reliance made the Whittle-Tang knife more than a possession. It was a partner in survival, a symbol of self-sufficiency and readiness. To be without one's knife was to be unprepared for the world, a sentiment echoed in the Old English saying about being caught with one's breeches down. In its worn handle and carefully maintained edge, we see the medieval world not as a distant, romanticized past, but as a hands-on, practical reality where a good edge and a trustworthy tool made all the difference in getting through the day. But if the scythe was the tool of the land and the knife the tool of the hand, the astrolabe was unquestionably the tool of the mind, a breathtakingly complex instrument that represented the absolute pinnacle of medieval science, mathematics, and craftsmanship. In an age often mistakenly characterized solely by superstition and subsistence, the astrolabe stands as a powerful rebuke, a shining brass testament to humanity's relentless drive to understand the cosmos and find our place within it. This was not a tool for farming or building. It was a portable planetarium, an analog computer, and a navigation device all in one, a sophisticated machine that allowed its user to hold a model of the very heavens in the palm of their hand, and by reading the stars, determine not only where they were on the earth, but also what time it was when the sun would rise, and even the direction of For prayer, it was in every sense a key that unlocked the universe. At its heart, the principle of the astrolabe was a brilliant act of cartographic projection. Its creators had to solve a fundamental problem: how to represent the three-dimensional dome of the sky onto a two-dimensional, flat plate of metal. They did this using a technique called stereographic projection, a complex mathematical concept that maps points on a sphere onto a plane. Imagine taking the celestial sphere with all its stars and the path of the sun, and projecting it outward from the North Pole onto a flat sheet. This intricate calculation resulted in the astrolabe's core component, the mother or mater, a thick, circular plate deeply recessed to hold other discs. Inside this recess, a user could place different latitude plates or climates, each one a custom-made map of the sky as seen from a specific geographic latitude. Engraved on these plates was a precise web of lines, the horizon line, altitude lines, and the azimuth lines representing compass directions. Over this plate rested the retere, the most visually stunning part of the device, a complex, web-like star chart cut from a separate sheet of brass, functioning like a rotating map of the most important fixed stars. The retere was a masterpiece of the metalworker's art, with pointers for individual stars that looked like delicate leaves and vines, and a large circle representing the ecliptic, the path of the sun through the zodiac constellations marked with the signs of the zodiac. This entire assembly was held together by a central pin, allowing the retere to rotate freely over the latitude plate, simulating the daily rotation of the stars around the celestial pole. Operating this intricate device was a skill that blended the knowledge of a scholar with the practiced hand of a sailor. The process began by taking a sighting. The user would hold the astrolabe by a ring at the top, allowing it to hang perfectly vertical. He would then sight a specific star or the sun through two vanes called alidades mounted on the back of the instrument. By aligning these vanes with the celestial body, he could read its altitude in degrees from a scale engraved on the back. With this single measurement in hand, the real work began. He would turn the instrument over and, knowing the date, rotate the retere until the pointer for that star or the position of the sun on the ecliptic ring matched the altitude line corresponding to the measured angle on the underlying plate. Once this alignment was achieved, the astrolabe became a functional model of the sky at that exact moment. He could now read the local time by the position of the retere against a scale on the rim. He could determine the time of sunrise or sunset for any day of the year. He could calculate the direction of prayer for a ship's captain on a cloudy night, losing sight of the North Star. He could even use the astrolabe to find it again by sighting on any other known star and working the device in reverse. This was not a simple tool. It was a puzzle box of the cosmos, and the user had to be both its operator and its interpreter. The creation of such a precise instrument was a task that demanded the highest levels of artistry and precision from the craftsman, known as an astrolabe. He was not merely an engraver, he was a master of astronomy, geometry, and metallurgy. His canvas was a disc of cast brass, which had to be perfectly flat and smooth. Using a complex set of dividers, rulers, and compasses, He would first lay out the hundreds of intricate lines and curves of the coordinate grid for the various latitude plates, a process that could take weeks of painstaking calculation and drafting. Each line had to be perfectly placed, as an error of a fraction of a millimeter could throw off a navigator's calculations by dozens of miles. Then, using a berin, a sharp, hardened steel graver, he would begin the incredibly delicate work of hand engraving these lines and the accompanying Arabic numerals and script onto the brass. The repair was an even greater challenge, requiring the craftsman to saw out the incredibly complex, lacy pattern by hand, often using tiny jeweler's saws. The final result was not just a scientific instrument, it was a work of art, often beautifully decorated with intricate Islamic geometric patterns or calligraphic inscriptions, a reflection of the culture where its design was most highly refined. The astrolabe's impact rippled far beyond the scholar's study. It was this tool that empowered the great age of exploration, both on land and sea. Islamic scholars and traders used it to navigate the vast, featureless deserts of Arabia and North Africa, their caravans guided as much by the stars overhead as by the dunes below. Later, European mariners adapted the principle into the simpler mariner's astrolabe, a heavier, more robust version designed to be used on the pitching deck of a ship, and it was this instrument that guided explorers like Vasco da Gama and Columbus across the terrifying emptiness of the open ocean. By providing a reliable way to determine latitude, the astrolabe gave these travelers the confidence to venture beyond the sight of land, to trust in mathematics and observation over folklore and fear. It shrank the world, connecting continents and cultures through expanding trade routes. More than any other object, the astrolabe symbolizes the true spirit of the medieval mind, not a dark age of ignorance, but a vibrant period of intellectual cross-pollination where ancient Greek knowledge was preserved and enhanced by Islamic scholars, translated into Latin and spread throughout Europe. It was a bridge between the library and the real world, a perfect fusion of abstract thought and tangible skill that literally guided humanity toward a brighter, more connected future. Yet for all the astrolabe's celestial complexity, the most elegant geometric designs of the medieval world were often born from a far simpler instrument, one that translated the perfect logic of mathematics into the physical realm with breathtaking clarity. This was the compass, the master of the circle and the arc, a tool that brought the divine concepts of symmetry and proportion down to earth for architects, artists, and engineers to wield. While we might associate it today primarily with navigation, its older and equally vital role was as a drafting instrument, the key that allowed the human hand to replicate the flawless geometry of the heavens in stone, wood, and parchment. In a world striving for order and beauty, the compass was the bridge between abstract mathematical theory and tangible, magnificent reality. The fundamental design was an exercise in beautiful simplicity, two arms joined at the top by a hinge with a sharp point on one end and a holder for a writing instrument on the other. But this apparent simplicity masked a profound requirement for precision manufacturing. The secret to a truly accurate compass lay entirely in the quality of that central hinge and the integrity of its points. A poorly made hinge with even the slightest bit of play or wobble would cause the legs to shift during use, resulting in a wobbly, imperfect circle that was useless for precise work. The hinge had to be impeccably crafted, often from brass for its resistance to corrosion and its smooth action, and fastened with a tight rivet that could be adjusted for tension. The points, too, had to be perfect. The fixed legs point was typically made of hardened steel, needle-sharp to bite into the surface of a vellum manuscript or a wooden planning board without slipping or tearing. The drawing leg held a piece of lead or a tiny reservoir for ink, and its tip also had to be meticulously maintained to ensure a consistent, unbroken line. A master craftsman's compass was a prized possession, often kept in a protective case and treated with the same care as a fine surgical instrument, for the accuracy of everything he built would ultimately depend on its flawless performance. With this trusted tool in hand, the medieval mind could begin to impose its grandest visions upon the world. For the architect designing a cathedral, the compass was the first tool he reached for. The entire layout of a Gothic church, from the sweeping curve of its apse to the intricate tracery of its rose windows, was fundamentally based on a series of interlocking circles and arcs. Using a massive compass with legs as long as a man's arm, he would scratch these primary geometric relationships onto a vast, flat plaster tracing floor, a full-scale blueprint from which every stone would later be cut. The proportions of the nave's width to its height, the relationship between the choir and the transepts, these were not arbitrary artistic choices. They were expressions of sacred geometry, believed to reflect the harmonious order of God's creation, and they were all discoverable through the relentless, logical application of the compass. This same tool was just as indispensable for the military engineer designing a new fortress. The ideal shape for deflecting cannon shot and eliminating blind spots was the bastion, a design that was essentially a complex series of angled points and arcs, all laid out with precise compass work to create a defensible geometric form. Beyond these monumental scales, the compass was the engine of detail and decoration. Illuminators working on priceless manuscripts used small, delicate compasses to frame their illustrations with perfect circular borders and to create the intricate geometric patterns that adorned the margins. Metalworkers used them to design everything from the complex hinges on a church door to the delicate filigree of a piece of jewelry, ensuring every curve was symmetrical and every element was in proportion. The tool's influence even extended to the creation of machinery. The design of water wheels, clockwork mechanisms, and the complex gears of a mill all began with compass-drawn circles, ensuring that moving parts would fit together and turn smoothly. In every case, the compass was more than a mere tool for drawing. It was a physical manifestation of the medieval belief in a universe governed by mathematical order, a way to bring a measure of celestial perfection into the imperfect world of human construction. It allowed for planning and predictability, reducing the risk of costly errors and enabling the creation of structures and objects of stunning complexity and harmony that continue to inspire awe centuries later. Yet for all the grand, sweeping arcs of the scythe and the celestial calculations of the astrolabe, some of the most crucial work in the medieval workshop was defined by a need for pinpoint accuracy on the smallest of scales. In the delicate art of joinery, where the strength of a piece often hinged on the integrity of a tiny wooden peg or a slender iron screw, a split piece of timber wasn't just an inconvenience, it was a catastrophic failure that could undo hours of meticulous work. This constant threat of splitting, especially when driving a fastener into dense, hard wood, demanded a solution of equal precision. That solution was the gimlet, a deceptively simple-looking tool whose brilliant, self-contained mechanism made it the undisputed master of starting the perfect small hole. At first glance, a gimlet might be mistaken for a corkscrew, and that comparison is not entirely off the mark. Its genius lay in its threaded, screw-like tip, a feature that fundamentally distinguished it from all other boring tools of the era. While an auger required significant downward pressure to cut and a bradawl simply pushed fibers aside, the gimlet operated on a principle of mechanical advantage. As the user pressed the sharp, threaded point into the wood and began to turn the cross handle, the screw tip did two things simultaneously. It drew the tool steadily into the wood with relentless, even pressure, and it actively carved out a clean, narrow channel for the body of the tool to follow. This screw action was the gimlet's great secret. It essentially pulled itself into the workpiece, requiring far less brute force from the user, and most importantly, ensuring the hole was started perfectly straight and true every single time. This was absolutely vital for tasks like starting a screw, where a misaligned hole would cause the screw to sit crookedly, weakening the joint and marring the appearance of the work. The true measure of a gimlet's quality, however, was forged in the fire of the blacksmith's workshop. Crafting this tool was a test of a smith's skill in working with small, intricate forms. The entire gimlet was typically forged from a single piece of good quality steel. The smith would first draw out the steel to form the shaft. Then, with careful hammer blows and the use of specialized swagers or formers, he would forge the finely pitched threads onto the business end. This required an incredibly steady hand and a keen eye. The threads had to be sharp, even, and continuous to bite effectively into the wood without tearing the fibers. The final and most critical step was the heat treatment. The threaded tip needed to be hardened to a glass-like state to maintain its sharpness through repeated use, but the long, slender shaft needed to retain some toughness to prevent it from snapping under the torsional stress of being turned in a tight hole. Achieving this differential temper, hard at the tip, tough along the shank, was the mark of a master smith. A poorly tempered gimlet would either dull instantly or snap in two, leaving its broken end frustratingly lodged deep within a piece of valuable timber. Once crafted, the gimlet became an indispensable part of a woodworker's or carpenter's portable toolkit. Its compact size and cross-handle design made it easy to carry in a leather pouch on a belt, ready for immediate use. This portability highlighted its role as a tool for precision and finishing, rather than heavy construction. A craftsman assembling a delicate piece of furniture, like a chest with locked joints or a chair with fitted arms, would use the gimlet to create a pilot hole for every single screw or nail. This preliminary step dramatically reduced the internal stress on the wood. Instead of a nail forcing its way through and violently pushing the wood fibers apart, which often led to a split radiating from the point of entry, the nail would now follow the pre-cleared path of the gimlet hole, sliding in with minimal resistance and leaving the surrounding wood perfectly intact. This attention to detail, this extra moment taken to prepare the material, was what separated rough carpentry from fine joinery. It was a practice born of respect for the material and a commitment to creating work that was not only strong but also flawless in its execution. The gimlet's legacy, therefore, is one of quiet perfectionism. It didn't create the grand structures or the sweeping curves of medieval craftsmanship. Instead, it perfected the countless unseen connections that held those creations together. In the neatly joined panels of a linenfold chest, in the firmly attached hardware of a castle door, or in the tightly assembled frame of a scholar's writing desk, the gimlet's contribution is invisible but absolute. It represents the medieval artisan's understanding that true strength and durability are built from the bottom up, beginning with a perfect, purpose-made hole no wider than a piece of twine. This humble tool ensured that the first step in any assembly was also the most sure, guaranteeing that everything built upon that foundation would be sound, secure, and built to last for generations to come. But after the scythe had done its work, laying the golden stalks of grain in neat windrows across the field, the real challenge began. Those precious kernels of wheat, rye, or barley were not simply loose and ready to be gathered. They were tightly encased within a tough, inedible husk and nestled at the top of a stiff straw stem. Separating the vital grain from this protective chaff was the next critical step, a task that fell to one of the most iconic and rhythmically satisfying tools of the harvest, the flail. This was not a tool of cutting or piercing, but of controlled, rhythmic impact, a device designed to deliver a specific kind of force that would break the bond between the edible seed and the inedible straw without crushing the precious cargo inside. In the relentless logic of food production, the flail was the essential bridge between the cut crop in the field and the miller's stone that would eventually turn it into flour. The design of the flail is a masterpiece of simple, effective physics, a study in how to amplify human force with a clever bit of engineering. It consisted of two separate wooden staves, each with a distinct purpose. The longer one, known as the handstaff or handle, was gripped firmly in the thresher's hands. The shorter, heavier one was the swipple or swingle, the business end that would deliver the beating. The true genius of the tool lay in the connection between these two pieces. They were never rigidly fixed together. Instead, they were joined by a flexible link, often a sturdy strip of leather or a short length of chain. This flexible hinge was the flail's secret weapon. It allowed the user to build up tremendous momentum by swinging the handle in a wide, overhead arc. At the precise moment of impact, the hinge allowed the swipple to pivot freely, snapping forward to strike the grain with a sharp, high-energy crack that was far more effective than a simple, rigid club could ever be. This design transferred the kinetic energy of the swing into a concussive blast that shocked the husks loose, while the flexibility prevented the kind of constant, jarring impact that would have quickly destroyed the thresher's wrists and elbows. Mastering this tool, however, was an art form in itself, a skill that went far beyond simply whacking a pile of straw. Efficient threshing was all about rhythm, precision, and a deep understanding of the material. The grain would be spread in a thick layer on a specially prepared, hard-packed clay floor, often inside a barn to protect the process from the elements. The thresher would then take his stance and begin a steady, metronomic motion, raising the flail overhead and bringing the swipple down squarely on the grain, not with wild, brute force, but with a focused, snapping impact. The goal was not to pulverize the straw into dust, but to deliver a sharp, percussive blow that would fracture the brittle husks and break the stems, allowing the heavier grains to fall to the bottom of the pile while the lighter chaff and straw remained on top. A novice would quickly exhaust himself with inefficient, poorly aimed swings, but an experienced thresher could maintain this rhythm for hours, his movements economical and precise, the sharp crack of the swipple striking the floor becoming the relentless, driving heartbeat of the autumn barn. This was back-breaking, monotonous work, and it was rarely a solitary endeavor. Threshing was often a communal activity, a task that brought together the workers of a village or a large farm. They would line up alongside each other on the threshing floor, their flails rising and falling in a staggered, interweaving rhythm to avoid tangling or striking one another. This created a powerful symphony of synchronized labor, a percussive soundtrack of coordinated cracks that signaled the progress of the harvest's final phase. There was a practical necessity to this teamwork. Threshing an entire harvest was a huge undertaking that benefited from many hands, but it also served a social purpose. The shared labor lightened the psychological load of the tedium, allowing for conversation, song, and a sense of shared purpose that transformed a grueling chore into a community event. The rhythmic, almost musical nature of the work lent itself to chants and work songs, helping to maintain the pace and pass the time. Once the beating was complete, the next step was separation, a process that relied on a different kind of tool and a helping hand from nature. The now mixed pile of grain, broken husks, and short straw, collectively known as the threshing, would be tossed into the air using a broad, flat winnowing basket or a fork. On a breezy day, the farmer would stand at just the right angle to the wind. The lighter chaff and straw would be carried away by the air current, drifting off to the side, while the heavier, denser grains would fall almost straight down into the basket or onto a cloth spread on the ground. This ancient practice, called winnowing, was the perfect partner to the flail's brute force, a graceful, almost magical-seeming final act that cleansed the grain and left it ready for the mill. The flail, therefore, was more than just a beater. It was the first and most physical act in the purification of the harvest. Its simple, effective design and the communal rhythm of its use ensured that the hard-won fruits of the field could be efficiently processed, securing the most vital commodity in the medieval world, the bread that would feed a family, a village, and ultimately, a kingdom through the long winter months. While the flail delivered its rhythmic beat on the threshing floor, another kind of rotation was happening in the workshop, one that was far more controlled and artistic, yet every bit as transformative. This was the domain of the lathe, a tool that didn't just shape wood, but enchanted it, spinning a stationary block of timber into a dynamic, symmetrical form right before the craftsman's eyes. To witness a medieval turner at work was to see a kind of magic, a rough, square billet of wood mounted between 2 points, beginning to whirl, and under the gentle pressure of a sharp tool, throwing off a continuous, delicate curl as a perfect, rounded shape emerged from the chaos. The lathe was more than a tool. It was a portal to a new dimension of woodworking, one where the only limit was the turner's own skill and imagination. The principle was as elegant as it was effective. At its heart, the lathe was a machine for imposing perfect symmetry. The wood to be shaped, known as the workpiece, was mounted on a central axis. On the simplest lathes, this axis was a setup between 2 fixed points, the headstock, which was often a simple spike, and the tailstock, an adjustable point that could be tightened to hold the workpiece firmly. This entire assembly was then connected to a drive mechanism. The earliest versions were the spring pole lathes, where a cord was wrapped around the workpiece and attached to a treadle on the floor and a flexible pole overhead. Pressing down on the treadle would pull the cord down, spinning the workpiece one way, and the spring of the overhead pole would then pull it back, returning the treadle to its original position for the next push. This created a reciprocal motion, a back and forth spinning, that required the turner to time his cuts carefully, making his move only on the downstroke. Later, the continuous rotary lathe emerged, powered by a hand crank or, more commonly, a foot treadle connected to a flywheel and a crank mechanism. This innovation provided constant, uninterrupted rotation in a single direction, a development that dramatically increased both the control and the speed of the work, allowing for smoother cuts and more complex design. But the true magic, the alchemy that turned spinning wood into art, happened at the point of contact between the sharp steel and the whirling grain. The turner's primary tools were his chisels and gouges, but these were a specialized breed, with long, sturdy handles and blades designed to be brapped against a metal rest positioned between the tool and the spinning wood. The turner wasn't pushing the tool, he was levering it, using the rest as a fulcrum to gain immense mechanical advantage and control. A master turner had a deep, almost spiritual understanding of how different woods behaved under the tool. Green, unseasoned wood was softer and easier to cut, but it would warp and crack as it dried. Seasoned wood was more stable but tougher on the tools. The secret, as always, was in reading the grain. Cutting with the grain resulted in a smooth, clean surface that seemed to polish itself as the tool passed over it. Cutting against the grain would tear out chunks, leaving a rough, ruined surface that could destroy hours of work in an instant. The turner had to feel the vibration of the tool, listen to the sound of the cut, and watch the emerging shape, all while maintaining a perfectly steady hand. It was a dance of intense concentration and profound sensory awareness. The objects that sprang to life from the lathe were a testament to its incredible versatility. At the most basic level, it was the only efficient way to produce any item that needed to be perfectly round. This included countless everyday essentials: wooden bowls and plates that were both lightweight and durable, sturdy chair and table legs that could be made identical for the first time, and countless tool handles for hammers, axes, and chisels, shaped to fit the hand perfectly. But the lathe also unlocked a world of intricate decoration and artistic expression. A skilled turner could create breathtakingly complex pieces like nested sets of goblets, delicate spinning tops for children, or the finely ballasted spindles for a noble staircase. By using a technique called eccentric turning, where the workpiece was mounted off-center, they could produce pieces with stunning, undulating patterns that seemed to defy the very logic of the machine that made them. The lathe allowed for a level of precision and repetition that was previously impossible, meaning a turner could produce dozens of identical chair legs or architectural finials, bringing a new level of refined uniformity to medieval interiors and structures. This leap in efficiency and artistry represented something far greater than just a new way to make things. It was a significant step on the path toward mechanization. The lathe harnessed human power through the treadle and flywheel to create a consistent rotary motion that could be applied to a manufacturing process. It wasn't just a hand tool, it was a machine tool, a platform that held the material and guided the cutting implement. This concept would eventually evolve, centuries later, into the powered machine tools that drove the Industrial Revolution. In the medieval context, the lathe was a glimpse of the future, a demonstration that human ingenuity could build devices to augment our own capabilities, not just with brute force, but with grace, precision, and an endless capacity for creating beauty from the most humble of materials. In the mesmerizing spin of the lathe, we see the medieval mind not only mastering its environment, but beginning to dream of the machines that would one day transform the world. While we often picture the quern as a star of the Renaissance printing press, its fundamental genius, the simple, brilliant principle of the adjustable wedge, was being forged in the pragmatic fires of the medieval workshop centuries earlier. This humble device, essentially a tapered block of wood or metal, was the unsung hero of precision, a master of tension whose sole purpose was to lock things into place with unshakable reliability. Long before it was ever used to secure a line of movable type, this same concept was already proving indispensable in the most vital trade of all, masonry. Imagine a master mason high on the rising wall of a cathedral. Each massive stone, meticulously carved, had to be set perfectly level and plumb before the mortar even hardened. But stones are rarely perfect, and settling could cause subtle shifts. The mason's solution was a wooden quern. He and his team would drive these small, tapered wedges into the narrow gaps around a newly placed block, carefully tapping them in sequence to apply minuscule, controlled pressure from multiple sides. This adjustable bracing would hold the stone in its exact, intended position, immovable against any accidental nudge, until the setting mortar could cure and permanently take over the load. This was the quern's first great role, a tool of temporary perfection, ensuring that the grand, gravity-defying vision of the architect was translated into reality with flawless accuracy, one perfectly locked stone at a time. The secret to the quern's remarkable effectiveness was a beautiful lesson in applied physics, a deep understanding of the wedge's mechanical advantage. The magic lay entirely in the precise angle of its taper. A wedge with too steep an angle would simply act like a chisel, wanting to split the material it was pressed against rather than applying steady, lateral pressure. But a wedge with a very shallow, long taper was a different beast entirely. Each light tap of the hammer would translate into a significant amount of lateral force, pushing the opposing surfaces apart with a smooth, controlled, and immensely powerful pressure. This allowed a craftsman to make incredibly fine adjustments. A tap on one coin might shift a stone a mere fraction of an inch, just enough to bring it into perfect alignment. This same principle of the adjustable wedge was applied across countless medieval trades. A wheelwright might use wooden quoins to securely lock the hub of a wagon wheel into a jig while he fitted the spokes. A shipwright could use them to hold a critical plank in position for drilling or fastening. In any situation where something needed to be held absolutely fast without permanent attachment, the quoin was the answer. It was the embodiment of the medieval craftsman's pursuit of reliability, a simple yet sophisticated solution to the universal problem of keeping things precisely where they were meant to be. This foundational work with physical wedges set the stage for one of the most pivotal moments in human history, the invention of the Gutenberg printing press around 1440. While the screw press itself was an adaptation of older wine and olive presses, the true revolution lay in the handling of the type. Each page was composed of hundreds of individual reversed metal letters, all painstakingly arranged by hand in a metal frame called a chase. This form then had to be placed in the press, inked, and subjected to immense, even pressure to transfer the ink to paper. The challenge was monumental. How do you ensure that not a single letter shifts, wobbles, or pops out under that tremendous force? A single loose piece of type would smash into its neighbors, ruining the entire form and potentially spraying precious, hand-cast metal type across the room. The solution, born from that centuries-old mason's knowledge, was the printing quoin. Gutenberg and those who followed him developed a specialized metal version of the tool. These were paired with a locking device called a planer, a flat piece of wood or metal that sat against the last line of type. The printer would place the quoins in the gaps between the edge of the chase and the planer, and then use a special key to gradually tighten them. With each turn, the quoins would drive the planer forward, pressing the entire form of type together from all sides, locking every single letter into a single, solid, immovable block of text. It was this innovation that made mass production of identical books possible. Without the quoin's ability to create perfect, adjustable, and releasable tension, the printing press would have been little more than a frustrating curiosity. The journey of the quoin, from a wooden block stabilizing cathedral stones to a precision metal tool locking ideas into place for mass distribution, is a powerful testament to the iterative nature of innovation. It highlights a crucial truth about the medieval period. It was not a dark void between ancient times and the Renaissance, but a vital incubator. It was an era where practical problems demanded practical solutions, and those solutions, like the adjustable wedge, were refined through daily use in the trades. These tools contained the seeds of future revolutions. The mason's need for stability directly informed the technology that would stabilize and disseminate knowledge itself, breaking the monopoly on information and ultimately empowering the scientific revolution and the Enlightenment. The quoin story reminds us that groundbreaking technology rarely appears out of thin air. It is most often a clever adaptation, a borrowed principle from one field that unlocks untold potential in another. It shows us that the drive for precision, for reliability, and for control over our materials is a timeless human impulse, one that built the great cathedrals of stone and then went on to build the even greater cathedrals of the mind. Now, if the auger was the tool for boring deep holes and the gimlet was the master of the screw starter, we arrive at the instrument that made both of those tasks possible in the first place, the bradawl. This was the tool of the very first mark, the initial commitment, the clean puncture that set everything else in motion. In a world without pre-printed templates or pencil lines that could be easily erased, the bradawl was the ultimate tool of precision, the device that translated a craftsman's careful measurement into a permanent, physical point of action. It was the sharp, decisive period at the end of the sentence of planning, the unambiguous signal that said, "Here and nowhere else." At first glance, it's easy to confuse the bradawl with its close cousin, the awl. Both feature a sharp metal spike set into a handle, but their purpose and, most importantly, their technique are worlds apart. An awl is designed to be worked with a twisting motion, its sharp edges cutting and parting fibers to create a hole for stitching, like a sailor using a marlinspike. The bradawl, however, is a straight-line instrument. Its primary function is to be placed exactly on a mark and then pushed with firm, controlled pressure directly into the material. Its blade is typically ground to a sharp, chisel-like point, not a round needle. This is its great secret. As you press it into wood, those sharp edges don't just push the fibers apart. They actually slice through them cleanly, severing the grain rather than just forcing it aside. This creates a clean, crisp, square-ended indentation that is the perfect starter hole for a screw or a guide mark for a saw. It prevents the wood from splitting along its grain line, a constant danger when driving in a fastener, because the fibers have already been neatly cut and contained within the boundaries of that initial mark. Mastering this tool was a lesson in applied pressure and profound patience. A novice, eager to get on with the real work, might lean into the bradawl with all their might, hoping to drive it deep in one go. This was a sure path to disaster. Too much force applied too quickly would overwhelm the wood structure, causing it to split violently, ruining a piece of carefully selected and prepared timber. The master craftsman knew a different way. He would position the bradawl's point with painstaking care, using the line he'd scored with a knife as his guide. Then he would apply steady, increasing pressure with the palm of his hand or the base of his thumb, feeling the resistance of the wood, listening to the faint crunch as the blade began to bite. He might rock the tool gently back and forth, not to twist it, but to help the chisel edge work its way deeper with minimal stress. This was a conversation with the material, a negotiation of force. The goal wasn't to conquer the wood, but to persuade it to create a perfect, clean beginning without a single splinter or crack. This meticulous, deliberate approach was the absolute hallmark of quality workmanship, the invisible foundation upon which every strong joint and beautiful finish was built. The applications for this small but mighty tool were endless. For the bookbinder, the bradawl was the first step in binding a priceless manuscript. He would use it to punch the initial guide holes through the entire stack of vellum pages and the leather cover, ensuring that when he followed with his stitching awl and needle, every hole would be perfectly aligned, resulting in a book that opened flat and whose binding would endure for centuries. For the carpenter fitting a hinge to a heavy oak door, the bradawl was the guarantee that his screws would go in straight and true. He would mark the positions for the screw holes, then use the bradawl to create a precise starter hole for each one, preventing the hard oak from deflecting the screw and ensuring the massive hinge sat perfectly flush against the wood. Even the cobbler used a form of bradawl to mark the placement of hobnails on a sole or to start holes for decorative stitching. In the final analysis, the bradawl represents a philosophy of craftsmanship that values preparation above all else. It is the tool that acknowledges that the most important part of any job is how it begins, that a moment taken for perfect precision at the start saves hours of corrective work or even catastrophic failure at the end. In the quiet, decisive push of the bradawl, we see the medieval artisan's deep respect for his materials and his process. He understood that before you can build, you must mark. Before you can join, you must measure, and before you can create something that will last for generations, you must make that first, perfect, intentional hole. But for all the elegant power of the draw knife, it presented a fundamental and dangerous problem. It required both hands to wield it effectively, leaving the craftsman with no way to securely hold the rapidly shifting, often awkwardly shaped piece of wood he was working on. Trying to clamp it to a standard bench was slow, impractical, and limited the angles of attack. The ingenious and brilliantly simple solution to this dilemma was the shave horse, a device that looked like a peculiar cross between a bench, a seesaw, and a torture rack, but was in fact one of the most ergonomically perfect work-holding tools ever devised. This was not merely a clamp, it was a dedicated partner in the shaping process, a foot-operated vise that transformed a solitary craft into a seamless, full-body collaboration between the woodworker and his tools. The design was a marvel of leverage and practical geometry, constructed entirely from wood, usually a tough, resilient hardwood like oak or beech for the critical stress points. The craftsman would sit astride a long, bench-like body, much like sitting on a low sawhorse, a feature that gave the tool its name. In front of him was a sloping platform where the workpiece would rest. The true magic, however, was operated by his feet. A long, wooden pedal or treadle was connected to a lever arm that ran under the bench. At the end of this arm, protruding up through a slot in the bench, was the clamp itself, a pivoting head called the dumbhead or clamping jaw. The secret to the entire system was a single, crucial pivot point. When the woodworker pressed down with his foot on the treadle, the lever arm would pull the dumb head forward and downward, pinning the workpiece firmly against the platform with a tremendous amount of mechanical force. The beauty of the mechanism was its natural release. Simply lifting his foot would instantly release the pressure, allowing him to quickly reposition the wood for the next series of cuts. This hands-free operation was revolutionary, granting the craftsman instant, adjustable, and incredibly powerful clamping force without ever having to let go of his draw knife. Mastering the rhythm of the shave horse was its own unique skill, a delicate dance between foot and hands that became second nature to an experienced woodworker. He would position a rough piece of wood, perhaps a half-split log, destined to become a barrel stave or a wagon spoke against the platform. A firm stomp of his foot would lock it in a death grip. Then, with both hands free, he would lean into the draw knife, pulling long, curling shavings towards his body, the wood held absolutely fast against the tremendous pulling force. After a few strokes, he'd lift his foot, give the wood a slight turn or advance it forward, and stomp again to re-clamp. This created a hypnotic, efficient rhythm: stomp, pull, 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 release, adjust, stomp, pull, pull, pull. This constant, subtle repositioning allowed him to work the entire piece evenly and symmetrically, something that would have been incredibly difficult and unsafe if he'd had to struggle to hold it by hand. The shave horse turned a potentially hazardous and awkward process into a smooth, controlled, and remarkably efficient operation. The impact of this tool on specific medieval industries cannot be overstated. It was the absolute cornerstone of the cooper's trade. A cooper building a barrel had to shape dozens of staves, each one with a complex, gently curved profile that had to fit perfectly against its neighbors. The shave horse allowed him to quickly and securely clamp each stave at every angle needed to create those precise curves with his draw knife. Similarly, the wheelwright relied on it to shape the long, tapered spokes that radiated from the hub of a cartwheel. For the chairmaker, it was essential for shaping the long, slender spindles for ladder-back chairs or the curved bows for Windsor chairs. Any craft that involved the repetitive shaping of long, slender, or curved components was utterly transformed by the speed and security the shave horse provided. It represented a massive leap in workshop efficiency, enabling a single craftsman to produce more, higher quality work with less fatigue and far greater safety, his tools and his body working in perfect, leveraged harmony. But after the flail had done its work and the grain was winnowed clean, the final and most critical transformation still remained. Those hard, dry kernels were a storehouse of potential energy, but they were utterly inedible in their raw state. To unlock their life-sustaining power, they had to be broken down, reduced to a fine powder that could be mixed with water and baked into bread. For a single family, the hand-powered quernstone was a daily grind of necessity. But for an entire village, a town, or a growing city, such a method was impossibly slow. The solution to this monumental challenge arrived not as a hand tool, but as a titan of engineering, the millstone. This was not a tool to be held, but a tool that held entire economies within its immense, grinding embrace. A device that harnessed the raw power of nature itself to perform the most fundamental task of civilization on an unprecedented scale. At the heart of every great watermill or windmill lay this colossal pair of stones, a partnership of immense weight and precision. The lower stone, known as the bedstone, was fixed solidly into the mill structure, an unmoving foundation of pure mass. Resting upon it was the runner stone, its identical twin in size but destined for a life of constant, slow revolution. This top stone was the one connected by a complex wooden gear train, called the gearing, to the great water wheel outside or the sweeping sails of the windmill above. The genius of the system was in the transfer of power. The gentle, relentless push of a river's current or the steady pressure of the wind was captured and multiplied through these wooden gears, transformed into the rotating force that could turn a stone weighing well over a ton. The gap between these two stones was the arena where the magic happened, a space so precisely controlled by the miller that it could be adjusted to the thickness of a coin. He would lower the runner stone using a lever mechanism, and into that narrow, dark space grain would be fed from a hopper above. What emerged from the perimeter was nothing short of alchemy, a continuous stream of warm, fresh flour, the very breath of a community. The true secret to the millstone's phenomenal efficiency, however, was etched across its surface in a mesmerizing, intricate pattern of grooves and planes. These carved channels, known as the furrows and lands, were the result of centuries of refinement and were the miller's most closely guarded knowledge. The pattern was far from random. It was a sophisticated system for managing the product within the grinding process. As the runner stone turned, the sharp, leading edges of the furrows acted like thousands of tiny scissors, slicing into the grain kernels. The progressively shallower angle of these furrows then performed a dual function. They provided a cutting surface for continued grinding, and they acted like conveyor belts, gently guiding the increasingly fine material outward toward the edge of the stones. The flat areas between the furrows, the lands, provided the crushing surface where the immense weight of the runner stone pulverized the grain against the stationary bedstone. This combination of slicing, grinding, and conveying happened in a single, continuous operation, a beautiful marriage of geometry and force that turned a simple pair of rocks into a highly efficient processing machine. The choice of stone for this monumental task was a science in itself. Not just any rock would do, it needed a very specific combination of hardness and porosity. The absolute pinnacle of millstone quality was a rock known as French burr stone. This wasn't a single, massive quarry stone, but a unique conglomerate, a natural concrete made of millions of small, sharp flint nodules cemented together by a limestone binder. This structure was the secret to its self-sharpening property. As the stones wore down from use, the slightly softer limestone binder would erode away just enough to constantly expose fresh, sharp flint edges, ensuring the stones remained voraciously efficient for decades. Because large, solid pieces of this stone were incredibly rare, the best millstones were actually puzzles. They were painstakingly assembled from dozens of individually quarried blocks of burr stone, each one carefully shaped and then bound together with iron bands and plastered with cement to form a single, seamless, monolithic grinding surface. This incredibly labor-intensive process made a set of true French burr stones a fantastically valuable asset, often worth more than the mill building itself. But even the finest stone would eventually wear smooth and lose its bite. This is where the miller's most vital and skilled trade came into play: stone dressing. This was a back-breaking, days-long process performed several times a year. Using a special set of pointed hammers called mill bills, the miller would have to recut the entire pattern of furrows and lands by hand onto the now smooth stone surface. This was not mere manual labor, it was a supreme act of geometry and artistry. The angle, depth, and spacing of every single furrow had to be identical and symmetrical, radiating perfectly from the center, or the stone would grind unevenly, produce a burnt-tasting flour, or worse, cause a catastrophic imbalance that could shake the entire mill to pieces. A master miller could judge the needed pattern by the sound the stones made while running and the feel of the flour they produced. This esoteric knowledge, passed from master to apprentice, was what separated a mediocre miller from a great one. His ability to maintain his stones directly determined the quality of the bread an entire community would eat, making him one of the most important and respected craftsmen in the medieval world. The impact of this technology rippled out far beyond the millpond. By industrializing the grinding process, the millstone single-handedly broke the bottleneck in food production. A single watermill operating continuously could produce more flour in a day than every household in a village could grinding by hand in a week. This abundance of affordable flour meant that even the poorest could access a more reliable supply of bread, the absolute staple of the medieval diet. This food security was the bedrock upon which populations could grow and towns could expand. The surplus generated by mills became a valuable commodity for trade, fueling local economies. Furthermore, the principles of gearing and power transfer perfected in the grain mill were quickly adapted for other industrial purposes: fulling cloth, forging iron, tanning leather, and crushing ore. The millstone, therefore, was more than just a tool for making flour. It was the original engine of industry, the first practical application of non-human, non-animal power on a massive scale. It marked the beginning of the end of subsistence living and paved the way for the specialized, trade-based economy that would define the modern world, all powered by the slow, inexorable, and monumental grind of stone upon stone. From the anvil to the millstone, these 30 ancient tools were far more than just objects of iron and wood. They were the very engines of daily life and the quiet architects of societal progress throughout the Middle Ages. Each one tells a story not just of function but of profound ingenuity, a testament to a world where human skill was the greatest technology available. The secrets behind their craft, passed down from master to apprentice in a continuous, unbroken chain of knowledge, reveal a culture of breathtaking innovation and meticulous dedication. This was a world where a blacksmith's understanding of tempering steel could mean the difference between a plowshare that lasted a season and one that fed a village for a generation, where a carpenter's mastery of the mortise and tenon joint could determine whether a cathedral's roof would stand for centuries. This deep, hands-on wisdom laid the essential groundwork for the technologies we often take for granted today. Every modern machine, every precision instrument, owes a debt to these foundational principles of leverage, material science, and mechanical advantage first perfected in the medieval workshop. By taking the time to understand these tools, we gain so much more than historical trivia. we develop a deeper, more visceral appreciation for the world our ancestors built with their own hands. We begin to see a castle not just as a static monument, but as a symphony of countless crafts. The stone perfectly squared with a level, the timber frames joined without a nail, the iron fixtures forged in a roar of bellows-driven fire. We can appreciate the loaf of bread as the final product of a revolution in agriculture powered by the heavy plow, harvested by the scythe, threshed by the flail, and ground by the millstone. We can feel the texture of history in the weave of cloth, created on a loom that was itself a marvel of engineering, its shuttle flying back and forth to build the fabric of society itself. This perspective connects us to the countless unnamed artisans whose collective skill and quiet dedication literally shaped the landscape of the past. We would love to hear which of these tools captured your imagination the most. Was it the celestial complexity of the astrolabe, a handheld model of the universe? Or the simple, brutal efficiency of the flail, turning the harvest into a rhythmic community effort? Perhaps it was the humble Whittle-Tang knife, an ever-present companion in a world of self-reliance. Share your thoughts in the comments below. Let's continue the conversation about these incredible instruments of history. If you enjoyed this journey back in time, be sure to subscribe and hit the notification bell so you don't miss our next exploration into the fascinating corners of the past. Thank you for watching, and may these stories of timeless ingenuity and painstaking craftsmanship inspire your own creativity.